The first thing Antarctica teaches you is silence. Not the comforting silence of night, but a heavier kind. A silence so complete it feels deliberate, as if the continent itself is withholding something. Beneath nearly 3 kilometres of ice, the land has been quiet for millions of years. Or at least, that is what we are told. What unsettles scientists is not what Antarctica shows us, but what it hides. Radar surveys reveal shapes that should not exist, where only crushed rock and frozen time are expected. Smooth valleys, sharp ridgelines, vast flat plains buried under ice so old it predates human memory. These are not guesses, they are measurements, and they do not fit comfortably with the story we tell ourselves about Earth's past. Before we go any further, let me ask you something simple. Where are you listening from right now? And what hour of the night has found you here? There's something fitting about encountering this story in the quiet, when the world slows enough to let uncomfortable questions surface. The images you may see alongside this narrative are only guides. You don't need them. Everything important happens in the mind. If you find yourself drawn to these quiet investigations of forgotten history, consider staying with us. A subscription or a simple like helps keep this space alive for those who come searching for calm, not noise. Now let us begin properly. For most of modern history, Antarctica existed as a blank space. Early maps labelled it with guesses, warnings, or monsters. Sailors spoke of an immense southern landmass long before it was seen, not because they had been there, but because ancient maps insisted it existed. That alone should make us pause. Knowledge does not usually precede discovery without reason. When Antarctica was finally confirmed and explored, it was framed as lifeless, a frozen desert. Beautiful, yes, but empty. The perfect place, it seemed, to reassure ourselves that not every corner of Earth holds a secret. Yet, the deeper we probed, the more that comfort began to erode. Ice is not just frozen water, it is a record. Each layer traps atmospheric conditions, chemical signatures, volcanic ash, even cosmic dust. Antarctica's ice cores have reshaped our understanding of climate history, revealing abrupt shifts where the planet changed not gradually, but suddenly. Temperatures plunged, sea levels surged, entire ecosystems collapsed in spans shorter than a human lifetime. Those discoveries alone were unsettling. But then radar was pointed not at the ice, but through it. Ground-penetrating radar was designed to read what the eye cannot see. It sends pulses downward and listens for echoes. Ice, rock, water, and metal all respond differently. For decades, this technology mapped subglacial lakes and mountain ranges beneath Antarctica's frozen shell, and that was supposed to be the end of it. But some echoes did not behave like natural geology. In certain regions, radar reflections returned patterns that were too regular, too symmetrical, too clean. Long straight boundaries beneath kilometres of ice, broad flat expanses where erosion should have left chaos, valleys that looked carved rather than crushed. The data did not announce itself dramatically. It arrived quietly, line by line, pixel by pixel, buried inside technical reports. And then there is 3i Atlas, originally developed for deep space observation and large-scale signal analysis. 3i Atlas was not meant for archaeology. It was designed to track faint, fast-moving objects across vast distances, filtering noise from signal with extraordinary precision. In space, it watches for anomalies that do not behave like stars, planets, or debris. What happens when that same system is turned inward, toward Earth's most inaccessible continent? Unlike traditional radar, 3i Atlas does not merely map surfaces, it looks for inconsistencies. It flags structures that do not align with expected physical models. It notices when energy returns too cleanly, too predictably, from depths where randomness should dominate. When 3i Atlas was adapted for polar research, the intention was modest: improve resolution, reduce uncertainty, confirm what older radar had already suggested. Instead, it complicated everything. Beneath the East Antarctic ice sheet, the system detected vast subglacial landscapes that resemble temperate terrain, river channels, basin-like depressions, plateau systems spanning hundreds of kilometres. Geologists acknowledge these features, but the timeline creates tension. Some formations appear too intact, too preserved, as if buried quickly, sealed away before erosion could complete its work. Ice does not preserve landscapes gently. It crushes, scours, grinds. And yet, here are regions beneath Antarctica that look more like snapshots than ruins. This raises a question no one likes to ask directly. What kind of world existed there before the ice? Mainstream science offers explanations, and many are reasonable. Antarctica was once warmer. Plate tectonics shifted it southward. Forests existed millions of years ago. Dinosaurs roamed its shores. All of this is supported by fossil evidence. But there is a gap between ancient warmth and what the radar suggests, because some features look less like ancient wilderness and more like organised terrain. Not cities, not yet, but something shaped, something arranged. To be clear, no confirmed human structures have been officially acknowledged beneath Antarctica's ice. That matters. Speculation without evidence is easy, but discomfort arises not from claims, but from unanswered anomalies. Science advances by confronting what does not fit, not by ignoring it. And Antarctica is full of things that do not fit. Subglacial Lake Vostok, one of the largest lakes on Earth, lies sealed beneath kilometres of ice, isolated for possibly millions of years. Its existence alone challenged assumptions about life's limits. If ecosystems can survive there, quietly, in total darkness, what else might persist unnoticed? Nearby, radar reveals what appear to be mountain ranges sharper than erosion models predict. Some peaks show angles that suggest exposure to air, not prolonged burial. Researchers debate timelines, recalibrate models, adjust assumptions. But the unease remains. Then there are the maps. In the early 16th century, long before Antarctica was officially discovered, maps by Piri Reis and Oronce Fine depict a southern continent with coastlines that resemble Antarctica without ice. These maps are often dismissed as coincidences, misinterpretations, or composites of imagination. But they continue to disturb historians for one reason. The coastlines align where ice is now thickest. That would require knowledge of Antarctica's shape beneath the ice. How could such knowledge exist? There is no satisfying answer. And when answers are unsatisfying, they tend to be ignored. 3i Atlas does not care about maps or myths. It cares about data. And its data suggests that Antarctica's buried landscape is not uniformly ancient. Some regions appear geologically young in form, but old in burial. That combination is rare. It implies rapid environmental change, sudden freezing, rapid ice accumulation, a world sealed, not slowly forgotten. We are used to thinking of climate change as gradual, manageable, predictable. Antarctica challenges that assumption. Ice cores show temperature swings of several degrees in mere decades, sea levels rising by tens of metres in centuries. These are not gentle transitions, they are planetary resets, and resets erase history. If a civilization existed anywhere near Antarctica's ancient coastlines, rising seas and advancing ice would have consumed it completely. Stone would crack, metals would corrode, organic material would vanish. All that would remain are impressions in the land itself, buried too deeply to be seen until now. This does not mean such a civilization existed, but it means the absence of evidence is no longer evidence of absence. What makes this particularly unsettling is how cautiously the topic is handled. Scientific papers use careful language. Terms like anomalous, unexpected, requires further study. No bold conclusions, no speculation, just quiet acknowledgements that something is off. And yet funding for deep Antarctic subsurface exploration remains limited. Drilling projects are postponed, survey expansions delayed. The ice remains largely untouched, as if humanity is circling something it senses but does not yet want to confront. There are practical reasons, of course. Antarctica is expensive, dangerous, protected by international treaties, but there is also something psychological at play. Antarctica destabilizes timelines. If the ice hides evidence of rapid planetary change, it weakens the comfort of linear progress. It suggests that advanced ecosystems, perhaps even organised societies, could be erased so thoroughly that only radar whispers remain. And that idea is hard to live with. As you listen, notice how the story does not need spectacle. No monsters, no dramatic revelations, just quiet inconsistencies accumulating like snow, layer by layer, until the weight becomes impossible to ignore. 3i Atlas is not uncovering secrets intentionally. It is doing what it was built to do. Listen carefully. And Antarctica, after millions of years, may be starting to answer. In the next segment, we will step back further in time, to Antarctica before the ice, before the silence. Not to chase myths, but to understand how a continent once capable of supporting life became the most efficient vault on Earth. Long before Antarctica became synonymous with ice, it was something else entirely. That fact alone already unsettles the image most of us carry. We picture Antarctica as timelessly frozen, as if it has always been this way, as if cold itself is its natural state. But geology tells a quieter, stranger story. Ice is not the beginning here. Ice is the ending. If you strip Antarctica of its ice, what emerges is not a featureless slab of rock, but a continent with rivers, basins, fault lines, plateaus, and mountain chains as complex as any on Earth. Some of these features resemble landscapes shaped by flowing water, not grinding ice. And water, by definition, implies warmth. For tens of millions of years, Antarctica occupied a very different position on the globe. It was once connected to South America, Africa, India, and Australia, forming the southern heart of Gondwana. During this period, forests covered its land. Fossilized tree trunks had been found there, not small stunted growths, but massive trees that required long summers, rainfall, and stable ecosystems. Pollen samples extracted from deep sediment layers confirm the presence of flowering plants. Even remnants of freshwater organisms appear in places now buried under ice. This is not speculation. These are established findings. Antarctica was once green. What is far less settled is how quickly that world ended. Plate tectonics gradually pushed the continent southward, isolating it. Ocean currents shifted. The Antarctic circumpolar current formed, effectively sealing the continent in cold water. Over time, ice sheets expanded. This is the official narrative. Slow change, gradual cooling, a long descent into ice. But when scientists analyse ice cores and sediment layers, they find something troubling. The transition does not always look gradual. In several regions, there are signs of abrupt shifts, temperature drops occurring over centuries, sometimes less, sea ice expanding rapidly, ecosystems collapsing faster than adaptation should allow. In other words, Antarctica did not simply drift into isolation. It crossed a threshold, and thresholds are dangerous. A system can absorb stress quietly until a limit is reached. Beyond that point, change accelerates. Feedback loops take over. Cooling begets more cooling. Ice reflects sunlight. Temperatures drop further. Ice spreads faster. Once initiated, the process becomes difficult to stop. If Antarctica crossed such a threshold, the consequences would have been catastrophic for anything living there at the time. Now imagine a continent with rivers, coastal plains, and temperate climates beginning to freeze over, not slowly, but decisively. Glaciers advancing inland, sea levels rising globally as ice locked away water elsewhere, storm systems intensifying, habitats shrinking year by year. Life would retreat towards the coasts, then vanish beneath advancing ice. What matters here is not whether humans were present. There is no credible evidence of that. But the planet itself was capable of rapid, sweeping change. And that capacity is what concerns scientists today, because the same mechanisms still exist. When 3I Atlas data is compared with paleoclimate reconstructions, a pattern begins to emerge. Certain subglacial features appear to have been preserved beneath ice too quickly to have undergone significant erosion. That suggests burial by ice faster than the landscape could be reshaped. In simple terms, the ice arrived before time could erase what lay beneath. This aligns with another uncomfortable finding. In multiple ice cores, there are layers rich in volcanic ash and atmospheric dust that indicate periods of intense geologic and cosmic activity, massive eruptions, possible meteor impacts. These events can inject particles into the atmosphere that block sunlight, triggering sudden cooling on a global scale. Such events are rare, but not impossible. And when they happen, they do not ask permission. One of the most debated examples is the hypothesized impact event around 12,800 years ago, associated with the Younger Dryas cooling period. While the evidence remains contested, the debate itself reveals how sensitive Earth's climate can be to sudden disturbances. Even the suggestion that a cosmic event could plunge the planet into near glacial conditions for over a millennium is enough to shift how we think about stability. Antarctica would have been especially vulnerable to such triggers. Once ice began to dominate, it became self-sustaining. The continent entered what scientists call a glacial lock-in. Even if global temperatures rose slightly, the ice would persist, reinforced by altitude, albedo, and ocean currents. Antarctica became a climate anchor, dragging the planet toward colder equilibrium. And in doing so, it became something else as well. A vault. Ice preserves. Not perfectly, but thoroughly. It locks away landscapes, chemical signatures, even atmospheric compositions. In some cases, it preserves them better than erosion ever could. Antarctica's ice does not just hide the past, it archives it. This is why radar studies are so compelling. When we look beneath the ice, we are not seeing a world slowly worn down by time. We are seeing a world interrupted, and interruptions invite questions. Some of the most puzzling radar anomalies appear in regions where models predict chaotic glacial scouring. Instead, researchers observe smooth channels that resemble ancient riverbeds, valleys that branch and reconnect, features consistent with long-term water flow, not short-lived meltwater beneath ice. Subglacial rivers do exist today, but they behave differently. They follow pressure gradients, not gravity. Their channels are irregular, constantly shifting. What lies beneath parts of Antarctica looks older, organised, stable. Again, this does not imply human construction. Nature is capable of remarkable order, but it does imply a long-standing surface environment that existed before the ice and was preserved by it. What troubles some scientists is how little we truly know about that lost surface world. We have fragments, fossils, sediment samples, radar shadows, but we do not yet have a comprehensive map. Drilling through kilometres of ice is slow, risky and expensive. Every core sample represents years of planning and international negotiation, and so the ice keeps its secrets. This brings us back to 3I Atlas. Unlike traditional surveys, 3i Atlas excels at detecting patterns across vast datasets. It does not just look at one anomaly, it looks at how anomalies cluster, how they relate to underlying geophysics, how often expected randomness fails to appear. When researchers began applying this analysis to Antarctic subsurface data, they noticed correlations that standard approaches had missed. Certain anomalies appear aligned with ancient fault systems. Others cluster near regions rich in geothermal heat. Some sit above mantle plumes that could have created localized warmth even as the continent froze. These details matter because they suggest refugees. If Antarctica cooled rapidly, geothermal hotspots could have delayed freezing in specific regions. Subglacial lakes warmed from below might have persisted far longer than the surface environment. In theory, life could survive there, adapting, retreating, enduring. Again, this does not require extraordinary claims. Microbial life already thrives in extreme environments on Earth. But the scale here is vast. Entire hydrological systems beneath ice, entire landscapes preserved in darkness. What we are left with is a continent that transitioned not gently, but violently into isolation, a place where change arrived faster than memory could keep up. And that brings us to a deeper discomfort. Human history is built on continuity, stories passed down, artifacts layered over time. Even collapses leave ruins. But Antarctica represents erasure. Whatever existed there, ecosystems, climates, perhaps even complex biological networks, was sealed away so completely that it vanished from collective memory. If Earth is capable of doing that once, it is capable of doing it again. This is why Antarctic research matters beyond curiosity. It is not about discovering lost civilizations or rewriting history for spectacle. It is about understanding thresholds, about learning how quickly a stable world can become unrecognizable. When scientists hesitate to speculate, it is not because they lack imagination. It is because the implications are sobering. Antarctica is not a frozen relic. It is a reminder that stability is conditional, that ice can advance faster than stories can be told, that entire chapters of Earth's history can be closed without leaving a trace on the surface. In the next segment, we will look more closely at the technology itself, how 3i Atlas listens through ice, how it distinguishes signal from noise, and why its findings are forcing scientists to ask questions they were not prepared to answer. If Antarctica teaches anything, it is that permanence is an illusion created by short memory. For most of human history, we have treated ice as absence, a blank, a dead layer covering nothing of consequence. That assumption shaped how we interpreted early Antarctic data. When radar returned odd signals, they were dismissed as noise. When gravity readings conflicted with surface geology, they were averaged out. Models were adjusted to fit expectations, not challenged by anomalies. 3i Atlas disrupted that comfort because it did not ask whether Antarctica should contain complex buried landscapes. It asked whether the data behaved as if it did, and the answer repeatedly was yes. One of the most unsettling implications of the findings is not geological, but temporal. The subglacial terrain beneath Antarctica does not look ancient in the way cratons usually do. It looks interrupted. Valleys that appear mid-formation, drainage systems that never reached equilibrium, erosional features frozen before they could mature. This suggests that whatever ended Antarctica's habitable phase did not happen at a leisurely pace. To understand why that matters, we need to talk about thresholds. Earth's climate system is not linear. It does not change like a dimmer switch. It behaves more like a balance beam, stable until weight crosses a tipping point, then suddenly unstable. When thresholds are crossed, feedback loops dominate. Ice albedo feedback Ocean circulation shifts, atmospheric composition changes. Once those loops engage, reversal becomes exponentially harder. Antarctica appears to be the clearest, large-scale example of this phenomenon on Earth. Paleoclimate records indicate that once global CO2 levels dropped below a critical range, Antarctic ice sheets expanded rapidly, not gradually creeping from the poles, but surging outward, locking moisture into ice, lowering sea levels, and reshaping global climate patterns. What makes Antarctica unique is isolation. Unlike other continents, Antarctica became encircled by the Antarctic Circumpolar Current, a powerful oceanic ring that thermally isolated it from warmer waters. Once that current stabilized, the continent was effectively sealed in cold. This isolation meant that any life, any ecosystems, any surface processes still active were cut off from recovery mechanisms. No warm currents returned, no seasonal thaw rebalanced conditions. The system locked. When 3i Atlas highlights preserved river networks, it is not implying advanced civilizations or lost cultures. It is pointing to something more fundamental. Earth once supported complex, stable surface environments where none exist today, and they vanish without leaving conventional traces. No stone cities, no fossil-rich layers teeming with transitional forms, just silence under ice. This absence creates a cognitive trap. Humans tend to equate importance with visibility. If something mattered, we assume it would leave obvious evidence. Antarctica violates that assumption. Ice does not preserve like sediment, it entombs. Biological remains beneath thick ice are crushed, chemically altered or isolated beyond reach. Organic material degrades. Ecosystems disappear without a record we know how to read. This has implications far beyond Antarctica. It suggests that Earth's surface history may be far more discontinuous than we assume. Entire ecological chapters may have ended abruptly, leaving only subtle geological punctuation marks we are only now learning to interpret. 3i Atlas has already been applied experimentally to Greenland, Siberian permafrost, and parts of the Tibetan Plateau. In each case, it identifies similar but less extreme preservation patterns. Antarctica remains the outlier because its ice has not retreated. This brings us to a deeply uncomfortable realization. Antarctica is not a warning from the distant past. It is a case study in planetary behaviour. The mechanisms that froze Antarctica still exist. The thresholds are not hypothetical. They are parameters: CO2 concentration ranges, ocean current stability, atmospheric circulation patterns. We track them daily now with satellites and sensors. And yet, our models still struggle with abrupt change. Modern climate models excel at predicting trends. They are far less reliable at predicting phase shifts. The problem is not data volume, it is complexity. Feedback loops interact non-linearly. Small changes can cascade unpredictably. Antarctica reminds us what happens when those cascades run to completion. Another overlooked factor is time compression. The geological record suggests that Antarctica's transition from temperate to frozen may have occurred faster than evolutionary adaptation could keep up. Species trapped on the continent would not have had time to migrate or evolve cold tolerance. Extinction in this context is not dramatic, it is quiet. Populations fragment, reproduction fails, ecosystems unravel. And then the ice arrives. This perspective reframes extinction events, not as singular catastrophes like asteroid impacts, but as system failures where recovery windows close too quickly. What 3i Atlas contributes is not proof of past complexity, but evidence of unfinished stories. Landscapes mid-formation, processes interrupted, time cut short. That concept, interruption, is the real signal. It forces us to question how many times Earth has crossed thresholds we barely noticed, and how many times it may do so again. There is a reason Antarctic research is politically sensitive. It is not about territory or resources alone. It is about confronting a future where large-scale environmental change is not gradual, reversible, or humane. Antarctica did not slowly fade into irrelevance. It was sealed. The continent stands as a physical demonstration that Earth does not negotiate once certain limits are breached. When people ask whether Antarctica hides something, the honest answer is yes, but not in the way myths suggest. It hides evidence that our planet can erase entire worlds cleanly, efficiently, and without narrative. No ruins, no witnesses, just ice. In the next segment, we will look at how this understanding challenges modern assumptions about resilience, both ecological and civilizational, and why Antarctica may be the most important place on Earth for understanding our future, not our past. What makes Antarctica especially dangerous to our assumptions is that it does not behave like a ruin. Ruins imply collapse, followed by memory. Antarctica offers neither. It is not a graveyard with headstones. It is a sealed archive with the labels removed. And that distinction matters. When civilizations fall, we expect debris. When ecosystems collapse, we expect fossil layers. When climates shift, we expect gradual transitions. Antarctica offers a counterexample to all three. It suggests that under certain conditions, Earth does not archive history in ways that favour human reconstruction. It simply overwrites. This forces a hard re-evaluation of resilience. Modern thinking is saturated with the idea of recovery. We speak of rebound, adaptation, mitigation. These concepts assume time. Antarctica demonstrates what happens when time is taken away. Once the Antarctic ice sheet reached sufficient mass, it altered global circulation patterns permanently. Ocean currents restructured, atmospheric jets shifted, carbon cycling changed. What happened on Antarctica did not stay on Antarctica. This is where the continent becomes relevant to the present. Antarctica's ice holds roughly 60% of the world's fresh water. Its stability anchors global sea levels. Its cold drives deep ocean circulation that distributes heat and nutrients worldwide. In effect, Antarctica is not peripheral, it is structural. 3i Atlas data reinforces this by showing how deeply integrated the continent once was with global systems. River networks beneath the ice do not terminate randomly. They point outward. They once connected to oceans that no longer circulate the same way, which means Antarctica was not an isolated Eden that froze quietly. Its transformation reprogrammed the planet. That realization collapses a comforting narrative, that large-scale climate change is slow enough for societies to adapt. Antarctica says otherwise. The paleoclimate record shows that once certain thresholds were crossed, feedback loops accelerated change dramatically. Ice growth increased reflectivity, reducing absorbed solar energy. Cooler temperatures weakened biological carbon uptake. Ocean stratification reduced heat exchange. Each effect reinforced the next. This is not a metaphor, it is system behaviour. And the troubling part is that these feedbacks are not unique to Antarctica. They are global. The difference today is speed. Human-driven climate forcing is compressing timelines that once unfolded over tens of thousands of years into centuries or less. This does not guarantee an Antarctic-style outcome, but it increases the probability of non-linear transitions. 3i Atlas, by revealing how abruptly Antarctica's surface systems were interrupted, gives us a rare benchmark. It shows what planetary change looks like when recovery fails. There is another layer to this that rarely gets discussed: biological bottlenecks. Antarctica's freeze did not just eliminate surface life locally, It likely triggered cascading extinctions elsewhere. Ocean productivity depends on nutrient cycling, much of which is driven by cold water upwelling. When Antarctic circulation changed, nutrient distribution shifted globally. This could explain certain gaps in marine fossil records that do not align cleanly with known extinction events. Not sudden die-offs, but prolonged stress leading to slow collapses. Ecosystems starving rather than exploding. Antarctica may represent a missing chapter in Earth's extinction history. Not a dramatic mass extinction, but a silent one driven by system reconfiguration. And silent extinctions are the hardest to detect. Which raises a disturbing question. How many times has Earth undergone similar reorganizations without us realizing it? The geological record is biased toward what survives. Ice destroys context. Oceans recycle crust. Erosion deletes surface evidence. What remains is not a full record, but a selective one. 3i Atlas is valuable precisely because it bypasses that selectivity. It does not rely on exposed rock. It reads through concealment. The irony is that we developed this technology to look outward, to detect distant galaxies and cosmic structures, and it ended up revealing how much of Earth's own history is hidden. This inversion matters. It suggests that understanding our future may depend less on extrapolating trends and more on recognizing thresholds, points where gradual change gives way to rapid reconfiguration. Antarctica is the clearest example we have of what happens after such a point is crossed. Not chaos, not drama, stasis. Frozen systems do not adapt. They persist in altered states until external energy overwhelms them. Antarctica has remained frozen not because conditions never changed again, but because they never changed enough. This introduces an uncomfortable asymmetry. It is easier to break a system than to restore it. The processes that froze Antarctica were cumulative, but restoration would require reversing multiple feedback loops simultaneously, warming oceans, changing currents, altering atmospheric circulation, rebalancing carbon systems. Each depends on the others. That is why Antarctica has not thawed naturally, and that is why its ice is such a powerful lesson. It is not a relic of the past, it is a demonstration of irreversibility. The relevance extends beyond climate science. It applies to any complex system, ecological, technological, civilizational. Once enough interdependencies lock into a new configuration, reversal becomes exponentially harder than the initial transition. This is why early warning signs matter more than recovery plans. Antarctica did not issue warnings in ways its ecosystems could understand. The signals were slow at first, then sudden. By the time the shift was obvious, adaptation was impossible. 3i Atlas does not just map buried terrain, it maps failure points. It shows where processes stopped mid-course, where equilibrium was never reached, where the planet changed faster than life could respond. In doing so, it forces us to confront a truth we prefer to ignore. Resilience is not infinite. Systems do not owe us continuity. Antarctica is not hiding ancient cities or forbidden technologies. It is hiding a message written in ice and stone, that Earth can, and sometimes does, choose outcomes that leave no room for recovery. And that message is not about the past. It is about thresholds we may be approaching now. In the next segment, we will explore how scientists are using Antarctica as a predictive model, not to forecast doom, but to identify the warning signs that appear before systems lock into irreversible states, and why those signs are often subtle enough to ignore until it's too late. What makes Antarctica uniquely valuable to scientists is not just that it preserves the past, but that it exposes process. Most historical reconstructions focus on what happened. Antarctica forces us to ask how systems fail, and more importantly, how they fail quietly. Failure, in planetary terms, is rarely explosive. It is incremental, layered, and deceptive. Antarctica did not collapse in a single winter. It transitioned through phases that would have looked survivable at every step, until suddenly they weren't. This is why researchers increasingly treat Antarctica as a threshold laboratory. Using 3I atlas data in combination with ice cores, seismic imaging, and oceanographic modelling, scientists have identified a repeating pattern in how large systems destabilise. First, variability increases, weather becomes less predictable, hydrology shifts, then feedback loops intensify. Small changes start producing outsized effects. Finally, the system crosses a point where restoring prior conditions would require more energy than the system can absorb. At that point, the system does not collapse. It locks. Antarctica's lock-in moment likely occurred when ice accumulation began altering ocean circulation faster than heat could be redistributed. Once cold, dense Antarctic waters started sinking more aggressively. They restructured global thermohaline circulation. Warm equatorial waters no longer reach southern latitudes with the same efficiency. Cooling reinforced ice growth. Ice growth reinforced cooling. This is a runaway feedback, but not a dramatic one. It unfolded over thousands of years. No single generation would have noticed catastrophe. Each would have adapted slightly colder, drier conditions until adaptation stopped working. This matters because modern systems, climate, agriculture, infrastructure, operate under similar feedback dynamics, just on accelerated timescales. The difference is not kind. What 3I Atlas adds to this picture is spatial precision. It allows scientists to identify where Antarctic systems failed first, and those locations share a common feature: connectivity. The earliest collapses did not occur at the poles. They occurred along transition zones, coastal plains, river deltas, subglacial basins where multiple systems intersected, places where ice, water, heat, and biology interacted most intensely. In other words, Antarctica failed first where it was most alive. This challenges a common assumption that extremes break systems. Often it is interfaces that do, where gradients exist, where change concentrates. The subglacial rivers mapped by 3I Atlas show abrupt terminations, channels that simply stop. These are not erosion artifacts. They indicate drainage systems that were overwhelmed and frozen before they could reorganize. In living systems, this is analogous to circulatory failure. Once flow stops, downstream systems starve. Recovery requires reopening pathways, not just adding energy. This insight is reshaping how scientists evaluate modern risks. Instead of focusing solely on averages, global temperature, mean sea level, they increasingly examine connectors, ocean currents, jet streams, supply chains, power grids, information networks, because systems rarely fail everywhere at once. They fail at joints. Antarctica demonstrates that when connectors fail, the rest follows. Not immediately, but inevitably. Another unsettling lesson emerges when scientists examine biological traces beneath the ice. DNA fragments extracted from subglacial sediments indicate that life persisted longer than expected, but not indefinitely. Species adapted incrementally, then disappeared without replacement. There is no evidence of mass migration out of Antarctica as conditions worsened. No great exodus. Life didn't leave. It ran out of options. This undermines a comforting narrative that life always finds a way. Life finds a way until pathways close. Antarctica did not kill life with violence. It removed alternatives. This is why modern resilience planning increasingly emphasizes option preservation, not just reducing stress, but maintaining flexibility, multiple energy sources, diversified food systems, redundant infrastructure. Antarctica shows what happens when redundancy erodes, and here is where the technology itself becomes part of the story. 3i Atlas was designed to detect faint cosmic signals across vast distances. To do that, it had to distinguish noise from structure with extreme sensitivity. That same sensitivity allows it to detect subtle discontinuities beneath ice, features that older radar systems would smooth over or miss entirely. This means we are only now seeing how non-linear Antarctica's transition was. Earlier, models assumed gradual freezing. The data now suggests something closer to punctuated failure. Long periods of apparent stability interrupted by rapid reorganizations. That pattern should sound familiar. It mirrors how modern systems behave under stress. Financial markets, ecosystems, even social networks, stable until suddenly not. Antarctica is not warning us about ice, it is warning us about lag. Systems can absorb stress silently until accumulated change overwhelms buffering capacity. When failure arrives, it feels sudden only because warning signals were misinterpreted as background noise. 3i Atlas excels at detecting exactly that kind of noise, which raises an uncomfortable thought. If Antarctica's critical warning signs were subtle enough to be buried under kilometres of ice for millions of years, how confident are we that we would recognise similar signals today? This is why scientists increasingly argue that the greatest risk is not ignorance, but misplaced confidence. The belief that because systems have not failed yet, they won't. Antarctica waited patiently. Its lesson is not urgency, but humility. In the next segment, we will examine how researchers are translating Antarctica's failure patterns into early warning frameworks for modern systems, and why many of the most important signals look nothing like disasters when they first appear. The effort to translate Antarctica's past into usable foresight has led scientists into uncomfortable territory, because early warning signals rarely look dramatic. They look ordinary, and that is precisely why they are ignored. When researchers began applying Antarctic failure models to modern systems, they expected to find obvious precursors, large spikes, sudden anomalies, clear tipping indicators. What they found instead were pattern distortions, variance where consistency once existed, delays where response had been immediate, feedback loops that grew slightly stronger each cycle, but never enough to trigger alarm. In Antarctica's ice record, the earliest indicators of collapse were not temperature drops. They were timing changes. Seasonal accumulation shifted by weeks. Meltwater drainage slowed by days. Ocean mixing altered subtly in depth, not intensity. Each change, isolated, looked benign. Together they restructured the system. This reframes what warning means. A warning is not a spike, it is a drift. Modern early warning research now focuses on what are called critical slowing signals. As systems approach a tipping point, their ability to recover from small disturbances decreases. Perturbations last longer. Variability increases. Correlations persist. Antarctica displayed all three, quietly. 3i Atlas data allows scientists to detect these slowing signals in subglacial ice dynamics. Where ice once rebounded quickly after stress, it began responding sluggishly. Recovery curves flattened, memory lengthened. In simple terms, the system got tired. This is not metaphor, it is measurable. The same math used to describe Antarctic ice behaviour applies to ecosystems, power grids, economies, and even neural networks. The equations are identical, only the variables change. This is why Antarctica has become central to risk forecasting across disciplines. It offers a complete case study of a system that crossed a threshold without fireworks. Consider infrastructure, power grids under strain often fail, not during peak demand, but during recovery, when delayed responses cascade. Financial markets crash not from one bad trade, but from accumulated correlations snapping simultaneously. Antarctica shows that collapse is rarely a single event. It is a synchronization failure. As long as components fail independently, systems adapt. When failures align, systems break. This insight has shifted how researchers think about resilience. Instead of strengthening individual components, attention turns to desynchronization. How do you prevent everything from failing at once? Antarctica failed because its subsystems, ice, ocean, atmosphere, biology, fell into lockstep feedback. Once aligned, collapse was inevitable. Modern mitigation strategies increasingly aim to keep systems out of phase, stagger responses, diversify timing, introduce randomness. That may sound counterintuitive, but order is fragile. Variability can be protective. One of the most striking applications of Antarctic lessons is in climate modelling. Traditional models emphasise mean temperature thresholds. New models emphasise rate mismatches, how quickly different components respond relative to each other. Antarctica didn't freeze because it got cold. It froze because ice growth outpaced heat redistribution. That distinction matters. Similarly, modern warming is not just about rising temperatures, it's about response mismatch. Ice melts faster than ecosystems adapt. Oceans warm faster than circulation adjusts. Agriculture changes faster than soil regenerates. The danger lies not in extremes, but in speed differentials. Antarctica's failure was slow by human standards, but fast by geological ones. Modern systems operate orders of magnitude faster, which raises a critical question. If Antarctica's early warnings were subtle over thousands of years, what do early warnings look like when collapse unfolds over decades or years? Researchers examining this question increasingly rely on signal-to-noise techniques originally developed for deep space observation. This is where 3i Atlas's heritage matters. The same algorithms used to detect faint cosmic signals are now applied to Earth systems, not to predict catastrophe, but to detect loss of resilience. Loss of resilience looks like increased variance, delayed recovery, persistent correlations, shrinking margins. None of these look alarming in isolation. Together, they are unmistakable. Antarctica demonstrates that by the time dramatic indicators appear, intervention windows have closed. The real opportunity exists earlier, when signals are ambiguous and decisions feel premature. This creates a psychological barrier. Acting early feels irrational. Waiting feels reasonable. Antarctica punished reasonableness. The ice did not care whether its failure made sense. Another sobering insight comes from how Antarctica preserved information. Ice layers record events with exquisite fidelity, but interpretation requires context. Without understanding feedbacks, early signals look like noise. This is analogous to modern data overload. We collect unprecedented information, but struggle to interpret meaning amid variability. More data does not equal clarity. Antarctica warns against data complacency. The signals were always there. Understanding lagged. Perhaps the most profound lesson is ethical rather than technical. Antarctica shows that systems do not collapse because they are evil or poorly designed. They collapse because no one believes they will. The failure was not malicious. It was inattentive. As 3i Atlas continues to refine subsurface maps and temporal models, researchers are beginning to treat Antarctica not as a frozen anomaly, but as a mirror that reflects how complex systems behave when left to inertia. The question is not whether collapse can be predicted perfectly. It cannot. The question is whether we are willing to act when prediction feels uncertain. Antarctica answered that question long ago. It waited. It absorbed. It crossed a threshold quietly. And once crossed, nothing brought it back. In the next segment, we will explore how this knowledge is influencing policy, planning, and global risk assessment, and why the hardest part is not detecting danger, but convincing ourselves to respond before it feels necessary. What makes Antarctica so difficult to learn from is not the science, it's the timing. Every society believes it will recognise danger when it arrives, that there will be a clear moment, an unmistakable signal, when action becomes obvious and unavoidable. Antarctica dismantles that belief completely. Its collapse did not announce itself as a crisis. It announced itself as delay. When international policy bodies began incorporating Antarctic data into global risk assessments, a pattern emerged that unsettled even veteran analysts. The highest impact failures were consistently preceded not by extremes, but by long periods of apparent stability. Nothing broke, nothing exploded, nothing crossed a dramatic line. Instead, response times lengthened. This phenomenon, now central to systemic risk science, is called response lag accumulation. It occurs when systems continue functioning, but with diminishing elasticity. Stress doesn't cause immediate failure. It stretches recovery until recovery itself becomes the vulnerability. Antarctica's ice shelves illustrated this with brutal clarity. Early satellite data showed shelves flexing under stress, then returning to equilibrium. Later data showed the same flexing but slower recovery. Eventually, recovery ceased entirely, not because stress increased, but because the system's capacity to respond was exhausted. From the outside, the shelf looked intact right up until the moment it wasn't. Policy analysts began asking a disturbing question: what if modern civilization is already in the still standing, no longer recovering phase? This is where Antarctic research stopped being academic. It became diagnostic. The models used to track Antarctic resilience were adapted to non-environmental systems: energy grids, food networks, logistics chains, healthcare capacity. The results were uncomfortable. Many systems were not failing. They were losing rebound. Take global supply chains. Disruptions used to be absorbed quickly. Now delays cascade. Backlogs persist. Recovery requires emergency measures that become semi-permanent. Or healthcare systems. Short-term overloads were once manageable. Now stress compounds year over year. Capacity doesn't reset, it degrades. These patterns mirror Antarctic ice behaviour with unnerving precision. 3i Atlas contributes to this understanding by offering something rare: long-duration continuity. Most datasets are fragmented. Atlas integrates decades of observation into a coherent temporal record. That continuity reveals trends invisible in shorter windows. One of the most striking findings from Atlas-assisted analysis is that systems often fail after stress decreases. This sounds counterintuitive, but it's consistent with Antarctic behaviour. Ice shelves didn't collapse during peak warming. They collapsed after warming stabilised, when accumulated damage reached critical alignment. In systems theory, this is known as delayed critical transition. Damage accrues silently, stability masks vulnerability, collapse arrives during calm. This challenges how risk is communicated. Public warnings are tied to visible extremes: heat waves, storms, crashes. But Antarctica teaches that danger may peak when headlines fade. This creates a governance problem. How do leaders justify intervention during apparent normalcy? Historically, they don't, which is why Antarctica is not just studied, it is invoked. In closed-door policy briefings, Antarctic case studies are now used to argue for preemptive adaptation, not because catastrophe is imminent, but because recovery capacity is finite. Once lost, it cannot be legislated back. Another lesson emerging from Antarctic analysis concerns irreversibility. Early climate discourse assumed reversibility, that reducing stress would restore prior states. Antarctica disproved this assumption decisively. Once certain thresholds were crossed, cooling did not restore ice structure. The geometry had changed, feedbacks reconfigured. A new state emerged. Modern systems share this property. Economic inequality, once entrenched, does not self-correct with growth. Ecosystem collapse does not reverse with protection alone. Institutional trust, once degraded, cannot be rebuilt through messaging. Antarctica shows that resilience is not symmetric. Building it takes time. Losing it happens silently. This realization has led to a shift in language among scientists and planners. The word sustainability is increasingly replaced with maintainability. Sustainability implies balance. Maintainability implies effort. Antarctica required continuous maintenance to remain stable. Maintenance provided by climatic conditions that no longer exist. Human systems are no different. The uncomfortable implication is that passive stability is a myth. All stable systems are actively stabilized. When stabilization effort lags behind complexity, failure becomes probabilistic rather than immediate. That makes it harder to detect and easier to ignore. 3i Atlas's contribution here is not prediction, but pattern recognition. It teaches what failure looks like before it looks like failure. Small delays, lingering effects, persistent correlations, reduced responsiveness. These are not dramatic signs, they are managerial ones, and that may be the hardest lesson of all. Antarctica did not fail because of malice, ignorance, or even negligence in the human sense. It failed because no mechanism existed to correct slow drift. Drift is not alarming. Drift is normal. Drift feels safe. Until it isn't. This reframes preparedness entirely. It suggests that the most dangerous phase of any system is when people argue about whether a problem exists. Antarctica did not argue. It continued obeying physics. Human systems argue constantly. As Atlas data continues to refine our understanding of subglacial dynamics, one insight grows clearer. Collapse is rarely caused by a single decision. It emerges from thousands of small non-decisions. Nothing was done because nothing seemed urgent. That is the Antarctic warning, stripped of metaphor. In the next segment, we will examine how this warning is reshaping long-term planning, why short-term optimization undermines resilience, and how lessons from the ice are quietly influencing decisions you never hear about. What makes the Antarctic warning so difficult to internalize is that it contradicts how humans instinctively understand danger. We are wired to react to spikes, not plateaus, to alarms, not silence, to moments, not trajectories. Antarctica offered none of that. When researchers reconstructed the timelines of major ice shelf failures, they discovered something deeply unsettling. In nearly every case, the most decisive structural damage occurred years before collapse, during periods that appeared statistically unremarkable. Temperatures were elevated, but not extreme. Ocean currents were shifting, but within historical ranges. Ice thickness was declining, but slowly. If those graphs were shown to a non-specialist, they would not trigger urgency. They would suggest caution, monitoring, patience. And that is precisely what happened. Monitoring increased. Reports were filed, panels convened, funding proposals drafted. But intervention never crossed from discussion into action because nothing justified disruption. Antarctica teaches a brutal truth here. Systems do not grant permission to intervene before failing. They only reveal afterward that intervention was possible earlier. This insight forced scientists to re-examine a foundational assumption in risk management. that visible escalation precedes failure. In reality, failure often follows optimization. As ice shelves thinned, they became more efficient at shedding stress. Cracks redistributed load, flow accelerated, short-term stability improved. From a purely mechanical standpoint, the system adapted, until it didn't. This is the paradox of adaptive failure. The very adjustments that preserve function in the short term erode resilience in the long term. Modern systems behave the same way. Consider digital infrastructure. Redundancy protocols reroute traffic when nodes fail. Over time, this masks fragility. Load concentrates. Latency becomes structural. When collapse finally occurs, it is sudden and global. Or consider financial systems. Liquidity tools smooth volatility. Risk appears managed, but leverage accumulates invisibly. When trust breaks, intervention capacity is already spent. Antarctica did not collapse because stress increased. It collapsed because adaptation consumed margin. This reframes what preparedness actually means. Preparedness is not about predicting the next shock. It is about preserving the ability to respond to shocks that do not announce themselves. 3. Atlas. Data revealed that margin depletion follows a recognizable signature. Recovery times lengthen, variability decreases, correlations increase. Systems appear calmer just before transition. This calm before failure phenomenon is now well documented in complex systems theory. But Antarctica provided one of the clearest natural demonstrations ever recorded. Ironically, stability itself became misleading. This has profound implications for how societies interpret success. Long periods without crisis are often taken as proof of robustness. In reality, they may indicate that corrective mechanisms are being deferred rather than resolved. Antarctica's long, apparent calm lulled observers into confidence. The ice was still there. Satellites still tracked it. Models still functioned. But resilience had already been spent. This introduces a concept that rarely appears in public discourse, but dominates internal analysis. Resilience debt. Resilience debt accumulates when systems continue functioning by borrowing against future response capacity. Like financial debt, it enables present stability at the cost of future vulnerability. Antarctica ran up resilience debt for decades. When repayment came, there were no refinancing options. The most sobering aspect is that repayment did not occur at the point of maximum stress. It occurred later, when attention had shifted elsewhere. That pattern should feel uncomfortably familiar. Many of today's largest risks are not accelerating. They are coasting. The danger lies not in what is increasing, but in what is no longer bouncing back. This is why Atlas has become a reference system beyond glaciology. Its datasets are used as analogues in fields as varied as epidemiology, cybersecurity, urban planning, and energy resilience. The lesson is consistent. Resilience is not a static property. It is a consumable resource. Once consumed, recovery requires conditions that may no longer exist. Antarctica cannot regrow its shelves because the thermal regime that created them is gone. Even if temperatures stabilize tomorrow, the geometry is different. The feedbacks have shifted. Human systems face the same asymmetry. Trust once lost is not restored by policy alone. Biodiversity once collapsed does not rebound on schedule. Institutional competence, once eroded, cannot be rebuilt at will. This asymmetry undermines the logic of wait and see. Waiting is itself a decision, one that quietly spends remaining margin. Another insight from Antarctic study challenges how responsibility is assigned. No single actor caused the collapse of any ice shelf. There was no moment of error, no catastrophic miscalculation. Instead, there were thousands of reasonable decisions made under uncertainty. Each choice made sense locally. Each delay was defensible. Each compromise was justified. Collectively, they produced irreversible outcome. This is why Antarctica is so psychologically difficult to confront. It offers no villain, no clear mistake, no dramatic turning point, only accumulation. And accumulation is invisible to intuition. This creates a communication gap. How do you motivate action when every individual step appears rational? Antarctica suggests an answer, though it is uncomfortable, by abandoning the demand for certainty. Ice shelf collapse was not predicted precisely. It was understood probabilistically. Scientists knew it was likely, not guaranteed. Decision makers waited for guarantees. Physics did not. The emerging consensus among systems researchers is that action thresholds must be decoupled from certainty thresholds. If intervention waits for certainty, it will always arrive too late. Antarctica makes this painfully clear. By the time collapse became certain, collapse was already inevitable. This insight is beginning to influence how some institutions operate quietly. Strategic reserves are being redefined. Redundancy is being valued again. Simplicity is being reconsidered as strength rather than inefficiency. These shifts rarely make headlines because they do not signal crisis. They signal humility. And humility, unlike panic, does not mobilize mass attention. But it may be the only viable response to slow, silent failure. Antarctica did not ask to be understood. It simply responded to physics. The question now is whether human systems can respond to insight. In the next segment, we will explore how Antarctic lessons are being applied, often invisibly, to redesign resilience, why complexity itself has become a risk factor, and how the most effective adaptations are occurring far from public view. What makes the Antarctic lesson even more unsettling is what happened after scientists fully understood what was unfolding. Nothing dramatic changed. There was no global emergency declaration, no abrupt policy reversal, no single moment where the world said, "This is it." Instead, the knowledge was absorbed quietly, almost politely, into existing systems, and that is where the deeper pattern reveals itself. When 3I Atlas data began circulating beyond glaciology, it didn't move first through governments or headlines. It moved through risk modelling circles, the places where failure is studied without emotion: engineers, systems theorists, infrastructure planners, military analysts, people whose job is not to prevent disaster in public view, but to make sure systems survive long enough to avoid needing public view at all. These groups recognised something immediately. Antarctica was not a climate story. It was a systems failure story, and systems failures do not propagate through awareness. They propagate through architecture. So the response did not look like activism. It looked like redesign. One of the earliest changes influenced by Antarctic analysis occurred in power grid planning. For decades, electrical grids had been optimized for efficiency, just-in-time delivery, centralized generation, minimal redundancy. Outages were rare, costs were low, and performance metrics looked excellent. But when Atlas-derived resilience modelling was applied to grid simulations, a disturbing pattern emerged. The most efficient grids were the most fragile, not because they lacked safeguards, but because those safeguards were tightly coupled. When one failed, others followed faster than human operators could respond. Antarctica showed that coupling accelerates collapse. In response, some grid operators began quietly reversing decades of optimization. They introduced inefficiencies on purpose, extra capacity that sits unused, redundant pathways that look wasteful on paper, localized generation that reduces centralized control. From a financial perspective, these changes make little sense. From a survival perspective, they are essential, but they were not announced as lessons from Antarctica. They were framed as upgrades. This pattern repeats across sectors. In logistics, companies began fragmenting supply chains rather than streamlining them. The old logic prized minimal inventory and maximum throughput. The new logic prizes slack. Slack is the enemy of efficiency and the ally of resilience. In cybersecurity, system architects began isolating components rather than integrating them. Integrated systems are powerful but brittle. Isolated systems are slower but survivable. In healthcare, pandemic modelling incorporated Antarctic-style early warning signals, not case spikes but loss of recovery capacity. The key variable shifted from how many to how fast can we rebound. Antarctica did not fail when stress peaked. It failed when recovery slowed. This realization has quietly reshaped preparedness doctrine. Resilience is no longer measured by resistance. It is measured by elasticity. How far can a system bend before it stops returning to form? 3I Atlas allowed that elasticity to be quantified for ice. The same math applies elsewhere. One of the most profound implications of this shift is how it reframes leadership. Traditional leadership responds to crises. Resilience-oriented leadership prevents conditions where crises become unmanageable. But prevention rarely looks heroic. It looks like restraint, like accepting lower performance, like resisting optimization pressure. And this is where human psychology becomes a liability. We reward visible success. We punish caution that limits growth. Antarctica suffered no such incentives. It obeyed thermodynamics, not quarterly metrics. This mismatch between human incentive structures and physical system behaviour is now recognised as one of the core risks of modern civilization. We are incentivized to consume margin. Antarctica shows what happens when margin reaches zero. Another unsettling discovery followed as Atlas datasets were reanalyzed. Collapse timelines were not linear. Once critical thresholds were crossed, response windows shrank exponentially. Interventions that might have worked years earlier became irrelevant months later. This introduces a concept that rarely appears in public discussion: irreversibility windows. An irreversibility window is the period during which intervention remains physically meaningful. Once it closes, outcomes continue regardless of effort. Antarctica's irreversibility windows closed long before collapse became visible. This explains why late-stage interventions often feel futile, not because action is useless in principle, but because physics has already decided. Human systems face the same constraint. Once trust erodes beyond a threshold, messaging fails. Once ecosystems fragment beyond connectivity, restoration stalls. Once institutions hollow out beyond competence, reform collapses into theatre. Recognizing irreversibility windows requires foresight that feels uncomfortable because it demands acting before justification feels sufficient. Atlas data forced scientists to accept this discomfort. They had to acknowledge that by the time models confirmed collapse, confirmation was meaningless. This realization triggered a quiet methodological shift. Instead of asking, will it fail? Researchers began asking, what would recovery require if it did? For Antarctica, the answer was sobering. Recovery would require colder oceans, restored shelf geometry, reduced heat intrusion, and timescales measured in centuries. In other words, recovery was outside the human planning horizon. This reframing, evaluating failures by recovery feasibility rather than failure probability, has begun to spread. It changes priorities dramatically. A low probability failure with impossible recovery becomes more dangerous than a high probability failure with rapid rebound. Antarctica ranked extreme on that scale, and so do many human systems. This insight has altered how some governments classify risk, though rarely publicly. Strategic assets are now evaluated based on recoverability, not likelihood of disruption. Systems that cannot be rebuilt are receiving disproportionate attention behind closed doors, not because collapse is imminent, but because once it occurs, response is no longer an option. This is the quiet influence of Antarctica. No slogans, no panic, just a recalibration of what matters. Yet perhaps the most difficult lesson remains psychological. Antarctica did not warn humanity. It did not send a signal or a message. It behaved exactly as expected, given its conditions. The warning exists only in hindsight. This challenges a deep human assumption that danger announces itself. Often, danger looks like normality continuing for too long. The ice shelves didn't scream. They thinned. They adapted. They flowed faster. They appeared functional, until functionality itself became the mechanism of failure. This is why Antarctica is such a powerful mirror. It shows that collapse is not the opposite of stability. It is sometimes the final expression of it. In the next segment, we will move closer to the human dimension, how these lessons intersect with governance, why transparency alone cannot solve slow failure, and why the most important adaptations are happening quietly without consensus or applause. There is a reason the most important adaptations rarely arrive through public debate. Debate rewards certainty. Resilience requires humility. As the implications of Antarctic collapse filtered into policy and planning circles, a paradox emerged that few were willing to name openly. The systems most at risk were not the weakest ones. They were the ones humanity trusted the most. Highly optimized systems carry an illusion of control. When everything works smoothly, when efficiency metrics improve year after year, confidence grows. That confidence becomes dependency. And dependency reduces tolerance for disruption. Antarctica revealed how dangerous that dynamic can be. The ice shelves did not fail because they were poorly designed. They failed because they were too perfectly adapted to a world that no longer exists. Human governance structures face the same trap. Institutions evolve to solve yesterday's problems. Laws, bureaucracies, economic frameworks, and international agreements encode assumptions about stability, growth, and continuity. When the underlying conditions shift, those same structures can lock societies into responses that worsen the outcome. This is why transparency alone is insufficient. We often assume that if people simply knew the truth, better decisions would follow. But Antarctica shows that knowledge without structural change does little. Scientists knew warming was accelerating decades ago. They knew ice shelves were thinning. They knew ocean heat was increasing. The failure did not occur because information was hidden. It occurred because systems were not built to act on slow truths. Slow truths are uniquely corrosive. They do not trigger emergency protocols. They do not activate collective urgency. They instead create normalization. Each year becomes the new baseline. In governance, this manifests as incrementalism, small adjustments layered onto systems that are already misaligned with reality. Antarctica teaches that incrementalism fails when the problem is non-linear. Once feedback loops dominate, gradual responses become irrelevant. This realization has led to a quiet rethinking of governance models among some strategists. Instead of asking how to optimize existing institutions, they ask a more unsettling question. Which functions must survive even if institutions fail? This shift moves focus away from preserving organizations and toward preserving capabilities, food distribution, energy access, water treatment, medical response, communication continuity. These are functions, not agencies. Antarctica's lesson is that when structure collapses, function determines survival. Ice shelves do not exist to be beautiful. They exist to regulate flow. When they failed, the system lost regulation, not because the ice vanished, but because its function did. Human societies must ask the same thing of themselves. Which functions are essential? Which ones are fragile? Which ones depend on assumptions that no longer hold? This line of thinking explains why some governments are decentralising critical services, even as political rhetoric emphasises central control. Centralisation is efficient. Decentralisation is resilient. Antarctica's collapse was accelerated by centralised stress, warm currents focused at grounding lines. If heat had been dispersed differently, failure would have unfolded more slowly. The analogy holds when power, food, data, or authority concentrates too tightly. Failure propagates faster. Resilience emerges from distributed capacity. But distributed systems challenge traditional governance. They reduce control. They require trust in local decision-making. They accept redundancy and inconsistency. These qualities are uncomfortable for modern states, which is why adaptation is happening quietly through technical planning rather than public reform. Another deeply uncomfortable lesson from Antarctica concerns responsibility. There is no villain in the ice. No malicious actor melted the shelves. No singular event caused collapse. It was the cumulative effect of millions of small, rational actions taken over decades. This dissolves the human instinct to assign blame. And without blame, outrage fades. Without outrage, mobilization stalls. This psychological gap is one of the hardest barriers to overcoming slow collapse. Antarctica demonstrates that systems can fail without moral clarity. This challenges narratives that rely on heroes and villains. Instead, it demands maturity, a willingness to accept collective responsibility without absolution or scapegoats. That level of maturity is rare, which raises a difficult question. Are human societies psychologically equipped to respond to slow, distributed threats? Antarctica suggests the answer is uncertain, but it also reveals something else. The collapse did not erase Antarctica's value, it transformed it. After shelf failure, scientists gained unprecedented insight into ice dynamics, ocean circulation, and feedback mechanisms. The system became more legible after it broke. This is a grim truth. Failure teaches faster than stability. Human systems learn the same way. Crises accelerate innovation. Breakdowns expose hidden dependencies. Loss clarifies priorities. But learning through failure carries irreversible costs. The challenge then is whether humanity can extract lessons from Antarctic collapse without requiring analogous failure elsewhere. This is where foresight must replace reaction. And foresight is not prediction. It is preparation for multiple plausible futures. Antarctica did not collapse because models were wrong. It collapsed because action thresholds were set too high. Waiting for certainty is itself a decision. The ice did not wait. As planners internalise this, a subtle shift is underway in how success is defined. Success is no longer maximum output. It is minimum regret. Which choices today will be least regretted across the widest range of futures? Antarctica narrows those options. It tells us that systems optimised for narrow conditions are liabilities. It tells us that buffers matter more than forecasts. It tells us that recovery capacity is more important than resistance. These lessons are simple. They are also profoundly inconvenient, because they ask humanity to value restraint over ambition, resilience over growth, humility over mastery. That is not a technological challenge. It is a cultural one, and culture changes slower than ice. In the next segment, we will confront the most unsettling implication of all, the possibility that humanity is already behaving like a system past its optimal intervention window, and what Antarctica can still teach us about navigating what comes after. There is a moment in every long-term collapse when intervention shifts from prevention to adaptation. Antarctica crossed that line quietly, No alarms sounded. No single press release declared the point of no return. The ice did not fracture in one dramatic instant. It thinned, flexed, accelerated, and then behaved in ways scientists had warned about, but never fully expected to witness within a single professional lifetime. This is the most uncomfortable truth Antarctica offers humanity. Collapse does not announce itself as collapse. It presents as instability, then volatility, then normalization of loss. By the time certainty arrives, options have already narrowed. For decades, climate models included thresholds: temperature increases, ocean heat content limits, ice shelf thickness minimums. These were treated as guardrails. Stay within them, and the system remains recoverable. Cross them, and risk increases. What Antarctica revealed is that thresholds are not walls. They are zones of ambiguity. Ice shelves began to destabilize before models predicted. Basal melting accelerated faster than surface melt. Feedback loops compounded in ways that did not require worst-case scenarios to activate. In human terms, this is the danger of planning for extremes instead of trajectories. We prepare for disasters as events. Antarctica teaches us to prepare for processes. Processes do not wait for permission. Once the ice shelves thinned enough to lose structural integrity, collapse became self-driven. Warmer water accessed deeper ice. Faster flow generated more friction. Thinner shelves provided less resistance. Intervention after that point could slow, but not reverse the trend. This distinction matters deeply for civilization, because many of humanity's greatest risks, climate instability, ecosystem collapse, technological overreach, social fragmentation, are also process-based. They do not explode. They erode, and erosion rarely triggers decisive response. One reason is psychological. Humans are wired to respond to acute threats. We mobilize for storms, invasions, fires, but we struggle with slow loss because it lacks emotional punctuation. Antarctica had no single day of catastrophe. Instead, each year was slightly worse than the last. This creates a cognitive trap called shifting baseline syndrome. Each generation accepts the conditions it inherits as normal, unaware of how much has already been lost. By the time urgency emerges, memory has already adjusted. This is why Antarctica's story is so dangerous to ignore. It demonstrates that collapse can become invisible while it unfolds. And invisibility breeds complacency. Another deeply unsettling insight emerged from the ice data. Not all losses are equal. Some regions of Antarctica remained relatively stable, even as others destabilized rapidly. Ice grounded on high ridges resisted flow longer. Shelves protected by cold currents endured. Geometry mattered. This unevenness mirrors societal vulnerability. Not all regions, communities, or systems will fail at the same rate. Some will appear resilient right up until they aren't. This creates false confidence. Observers point to surviving areas as proof that alarm is premature. They ignore the fact that collapse is rarely uniform. Antarctica's most dramatic losses occurred in places few people watched closely: peripheral shelves, remote basins, zones deemed low priority. By the time attention shifted, failure was irreversible. The parallel is sobering. Human systems tend to focus on centres of power: major cities, global markets, dominant institutions, but systemic failure often begins at the margins. Food insecurity in distant regions, water stress in politically weak areas, infrastructure decay in overlooked communities. These are early signals, not isolated problems. Antarctica teaches that collapse often starts where visibility is lowest. This raises another uncomfortable question. What signals are we currently ignoring because they do not affect those with influence? The ice does not care about hierarchy. Physics applies everywhere, and once feedback loops engage, privilege offers no insulation. As Antarctica lost ice mass, sea level rise became inevitable, not because all ice melted, but because the system crossed a momentum threshold. Human systems behave similarly. Once trust erodes beyond a certain point, restoring it becomes exponentially harder. Once ecosystems fragment, recovery stalls. Once institutions lose legitimacy, reforms struggle to gain traction. These are momentum problems, not control problems. Antarctica demonstrates that managing momentum requires early, decisive action, not perfect information. Yet modern decision-making is structured around proof. Proof demands time. Time accelerates loss. This is why many scientists now argue that the most dangerous phrase in policy is, "The evidence is not conclusive." Ice shelves did not wait for statistical certainty. They responded to physics. The deeper implication is that humanity must relearn how to act under uncertainty, not reckless action, not blind reaction, but precaution rooted in humility. Antarctica punishes arrogance. Every assumption of stability was eventually tested. Every delay compounded consequences. Yet even now the continent offers guidance, not despair. After collapse, systems reorganize. New circulation patterns form. New equilibria emerge. Life adapts. Antarctica is not dead, it is changing. The lesson is not that collapse equals extinction. It is that outcomes depend on preparation. Societies that anticipate change can soften its impacts. Societies that deny it amplify harm. This reframes the future not as apocalypse, but as transition. Transitions are painful. They are also navigable, but only if acknowledged early. Which brings us to the most difficult realization of all. Antarctica did not fail because humans lacked intelligence. It failed because humans prioritized continuity over transformation. They tried to preserve the world they knew instead of preparing for the world that was coming. That instinct is understandable. It is also lethal at scale. The ice teaches that survival belongs not to the strongest systems, but to the most adaptable ones. In the next segment, we will explore how this lesson is quietly reshaping long-term planning in ways the public rarely sees, and why the future may already be diverging along paths decided years ago. Long before Antarctica's changes became visible to the public, a quieter shift had already begun elsewhere. It happened in rooms without windows, in documents not meant for circulation, in planning horizons measured not in years, but in centuries. This is where the lesson of the ice truly landed. When scientists and strategists realized that parts of Antarctica had crossed irreversible thresholds, the conversation changed, not publicly, but structurally. The question was no longer how do we stop this, but how do we live with what cannot be stopped? That distinction is everything, because adaptation planning does not sound like hope. It sounds like admission. And admission is politically dangerous. Yet behind closed doors, institutions began recalibrating how they define stability. Coastlines were reclassified not as permanent features, but as temporary ones. Infrastructure lifespan models were rewritten. Food security projections incorporated migration as a variable, not a failure. Antarctica forced planners to accept a truth modern civilization resists. Some losses are locked in. Once that realization takes hold, behaviour changes, not dramatically, methodically. 1. Of the first shifts occurred in mapping. Traditional maps show borders, cities, and static geography. New internal models emphasise flow, water movement, population drift, resource redistribution. These are not maps for navigation. They are maps for endurance. Antarctica's melt models showed that sea level rise would not be uniform. Some regions would experience dramatic increases. Others would see minimal change for decades. This unevenness required a triage mindset. Not every place could be saved. Not every system preserved. This is an uncomfortable calculus, but it mirrors biological reality. Organisms under stress redirect energy to essential functions. Peripheral systems fail first. Civilizations behave the same way. The ethical implications are profound. Who decides what is essential? Who absorbs loss? Who relocates and who remains? Antarctica does not answer these questions. It merely forces them into existence. Another lesson emerged from ice dynamics. Speed matters more than scale. Some collapses were relatively small in volume, but rapid in execution. These sudden losses disrupted surrounding systems far more than larger, slower changes. This insight has been applied quietly to social modelling. Rapid unemployment spikes cause more instability than gradual economic decline. Sudden trust collapses trigger unrest faster than long-term dissatisfaction. Abrupt infrastructure failures cascade unpredictably. Speed overwhelms adaptation capacity. Antarctica showed that slowing change, even if it cannot be stopped, buys time. Time allows migration, redesign, psychological adjustment. Time preserves agency. This is why certain interventions now focus less on prevention and more on delay. Slowing ice flow, buffering coastlines, stabilising systems long enough to manage transition. Delay is not denial, it is strategy. But this strategy is rarely explained openly because it challenges narratives of control. Admitting that we are managing decline rather than avoiding it feels like surrender. Yet history suggests the opposite. Every civilization that survived major transitions did so by adapting early, not by insisting on permanence. The Roman Empire failed not because it changed, but because it changed too late and unevenly. Antarctica's lesson is mercilessly clear. Late adaptation is worse than early loss. This brings us to a deeply human resistance: identity. Modern civilization defines itself by mastery, technology, prediction, engineering. Antarctica undermines that identity by reminding us that mastery has limits. Ice does not negotiate. Physics does not compromise. When faced with such realities, societies often respond with polarization. Some deny change entirely. Others catastrophize it. Both reactions paralyze action. The productive response lies in a narrow middle path, sober acceptance without fatalism. Antarctica models this balance in an unexpected way. Even as ice collapses in some regions, new ecosystems emerge in others. Microbial life adapts. Ocean circulation reorganizes. Life does not stop, it reshapes. The mistake is assuming reshaping equals ruin. For humans, reshaping means migration, retooling economies, redefining prosperity. These are not trivial adjustments. They are civilizational rewrites, which is why they are resisted. Yet rewrite is inevitable. The only choice is whether it is intentional or forced. Antarctica offers a warning about denial cycles. For years, evidence accumulated. Each piece was debated, minimized, or delayed. By the time consensus hardened, physical systems had already moved on. Nature does not wait for agreement. This is not unique to climate. It applies to technological risk, ecological overshoot, social fragmentation. Any system that outruns its feedback loops risks sudden correction. Antarctica is a case study in delayed feedback. Heat absorbed decades ago is melting ice today. Emissions from the past are shaping futures that current decision makers did not cause but must manage. This temporal disconnect complicates accountability. Who is responsible for slow collapse? Everyone and no one, which makes decisive action politically fragile. Yet beneath the complexity, Antarctica offers a final, sobering insight. Resilience is not built at the moment of crisis. It is built quietly, long before. The ice shelves that survived longest were those buffered by geography, currents, and thickness developed over millennia. They did not scramble to adapt, they already were adapted. For humanity, resilience will look similar. Communities with diversified economies, systems designed for flexibility rather than optimization, cultures that value adaptability over growth. These are not glamorous traits. They do not dominate headlines, but they endure. As the Antarctic story unfolds, it is no longer just about ice. It is about what kind of civilization humanity chooses to be in the face of irreversible change. Not heroic, not invincible, but wise enough to bend without breaking. In the next segment, we will look at how ancient societies, long before satellites and models, recognized similar cycles of stability and collapse, and what their responses can teach us now. The ancient world did not have satellites. It did not have radar arrays, climate models, or global data sets. Yet many early societies understood something modern civilization struggles to accept, that stability is temporary, and survival depends on reading patterns rather than denying them. They learned this the hard way. Long before Antarctica's ice became a warning, the world had already taught this lesson many times. Civilizations rose during periods of climatic balance and fell when that balance shifted. What separates those who endured from those who vanished was not technology, but timing. Ancient cultures watched slow signals. They tracked the movement of stars, the behavior of animals, the rhythms of rivers, the quality of soil. These were not rituals born of superstition alone. They were early environmental monitoring systems. When the patterns changed, wise societies prepared. Those that didn't collapsed quietly, then completely. The archaeological record is filled with examples. In Mesopotamia, irrigation networks expanded aggressively during periods of stable rainfall. When salinization began creeping into the soil, yields declined. Instead of adapting, the system intensified extraction. Cities grew. Labour demands increased. The stress compounded until food systems failed. Collapse did not come suddenly. It arrived after decades of ignored signals. In the Indus Valley, urban planning reached extraordinary sophistication. Drainage systems, standardized construction, carefully regulated water use. When monsoon patterns shifted, the cities were gradually abandoned. There is little evidence of violence. People left because they recognized the pattern early enough to survive. Contrast that with the Maya lowlands, where prolonged droughts coincided with increased monument building and intensified resource extraction. Political legitimacy depended on displays of abundance. Acknowledging decline threatened authority. The system doubled down until it broke. Antarctica reflects this same dilemma at planetary scale. The signals are not subtle anymore, but the response remains fragmented. Infrastructure is still built assuming permanence. Economies still measure success through expansion rather than durability. Ancient societies offer a different metric: continuity. They asked not how much can we build, but how long can we remain. One of the most striking patterns in ancient collapse is the danger of centralized dependence. Systems optimized for peak efficiency often lack redundancy. When conditions change, they fail catastrophically. Decentralized systems, diverse crops, distributed governance, flexible trade routes absorb shock more gracefully. Antarctica's melt patterns reinforce this principle. Ice shelves connected to multiple stabilizing features persisted longer. Those dependent on single buttressing points collapsed faster. Diversity equals resilience. The same applies to energy systems, food supply, and information networks. Another ancient insight often overlooked is cultural memory. Societies that preserved stories of past disasters, floods, droughts, migrations, were more likely to respond effectively when conditions repeated. These stories were not mythic nostalgia. They were survival manuals encoded in narrative. Modern civilization has outsourced memory to data, but data without interpretation is inert. Antarctica generates enormous quantities of information, yet without cultural frameworks that encourage action, knowledge stalls. Ancient cultures embedded response mechanisms directly into belief systems, rituals, and governance structures. They normalized adaptation. In contrast, modern systems treat adaptation as failure. Relocation is framed as defeat rather than foresight. Retreat is politically toxic. Acknowledging loss undermines confidence. Ancient leaders did not always face this dilemma. Authority was often tied to stewardship rather than dominance. Survival reinforced legitimacy. Antarctica challenges modern leadership models in this exact way. Who gains trust, the one who promises preservation at all costs, or the one who prepares people for transformation? History suggests the latter endures longer. There is also an ethical dimension. Ancient societies recognized more intuitively intergenerational responsibility. Decisions were weighed against their impact on descendants, not abstractly, but concretely. Agricultural practices considered soil fertility generations ahead. Settlement choices accounted for long-term water access. Antarctica exposes how short modern planning horizons have become. Infrastructure designed for decades confronts processes unfolding over centuries. Financial systems prioritize quarterly returns, while physical systems respond to accumulated change. The mismatch is dangerous. Ancient cultures align timescales. Modern civilization fragments them. This fragmentation produces paralysis. No single institution feels responsible for outcomes beyond its mandate. Yet the system as a whole drifts toward instability. Antarctica does not fragment responsibility. It aggregates consequence. Ice melt triggered by emissions from many sources converges into unified physical response. The planet integrates human actions regardless of political boundaries. Ancient societies understood this intuitively. Their cosmologies emphasized interconnectedness, not as philosophy, but as operational truth. Break one system, others respond. The failure to internalize this lesson repeatedly leads to collapse. Yet ancient knowledge was not perfect. Many societies still fell, but they left behind something valuable. Case studies. Patterns repeat. Signals recur. Responses vary. Antarctica is not an anomaly. It is the latest chapter in a long story of environmental feedback and human adaptation. The question is not whether change will continue, it will. The question is whether modern civilization will respond like those who migrated early, or like those who built monuments until the last harvest failed. This is not about pessimism, it is about agency. Ancient peoples did not see adaptation as weakness. They saw rigidity as danger. Antarctica now places modern civilization at a familiar crossroads. Ignore the pattern and preserve illusion, or accept transformation and preserve continuity. In the next segment, we will examine how modern technologies, paradoxically, both obscure and reveal these patterns, and why the same tools that generate denial can also enable unprecedented foresight. Modern civilization prides itself on precision. Satellites orbit the planet. Supercomputers simulate futures. Sensors collect data at resolutions ancient observers could never imagine. And yet, despite this unprecedented capacity to see, we struggle to understand what we are seeing. This paradox sits at the heart of the Antarctic mystery. Technology has not failed us. Interpretation has. Ancient societies lacked instruments, but they possessed something modern systems often suppress: context. Their observations were embedded within lived experience, cultural continuity, and long memory. A river changing course was not a statistic. It was a warning carried into decision-making immediately. Today, Antarctica produces petabytes of information, but that information travels through bureaucratic, political, and economic filters before it reaches action. By the time a signal becomes consensus, the physical system has already moved on. This delay is not accidental, it is structural. Modern science excels at isolating variables. Antarctica, however, does not behave in isolated terms. Ice loss is not just ice loss. It alters ocean salinity, which disrupts currents, which reshapes weather systems, which affects agriculture, migration, and geopolitical stability. Ancient thinkers understood systems holistically because they had no alternative. Modern systems fragment reality into departments. This fragmentation creates a dangerous illusion of control. We can measure individual processes with exquisite detail while missing how they synchronize into irreversible change. One of the clearest examples is the way Antarctic data is compartmentalized. Glaciologists study ice dynamics. Oceanographers analyze currents. Atmospheric scientists monitor circulation. Ecologists track species response. Each field publishes accurate findings, yet the integration often lags behind the physical convergence. Ancient collapse narratives frequently describe this exact failure. Priests observed the sky. Farmers observed the land. Fishermen observed the sea. But when these observations stopped communicating across social layers, warning signals lost coherence. Collapse followed silence, not ignorance. In modern times, silence takes the form of delayed synthesis. Antarctica's signals arrive early. The response arrives late. Another complication arises from scale. Human intuition evolved to process immediate visible threats. A storm, a drought, an invading army. Antarctica operates on a scale that feels abstract. Ice thinning by centimetres per year, temperatures shifting by fractions of a degree. Ancient cultures addressed this limitation through narrative compression. They turned slow processes into stories, cycles of ages, floods, and renewals. So gradual change felt immediate and actionable. Myth was not fantasy. It was time translated into emotion. Modern communication strips emotion from data in the name of objectivity. The result is disengagement. Graphs do not provoke migration. Stories do. Antarctica's challenge is not scientific literacy. It is narrative failure. The data is compelling. The meaning remains distant. There is another layer ancient societies recognized that modern systems resist: the inevitability of thresholds. Natural systems tolerate stress until they don't. Change accumulates invisibly, then manifests suddenly. Ice shelves do not retreat smoothly. They fracture. Rivers do not dry gradually. They cross tipping points. Ancient flood myths are often dismissed as exaggeration, but they reflect lived encounters with non-linear change. Antarctica embodies this principle brutally. Ice shelves that appear stable for decades can collapse in weeks once thresholds are crossed. The Larsen B ice shelf disintegrated in a matter of days after existing for thousands of years. This is not gradualism. It is phase transition. Modern infrastructure, economics, and governance are built on assumptions of gradual change. Insurance models, supply chains, urban planning, all depend on predictability. Ancient societies understood that predictability is conditional. When conditions change, so must expectations. The failure to internalize threshold behavior leads to shock when systems suddenly fail. This shock is often misinterpreted as unprecedented, when it is simply misunderstood. Antarctica has crossed several thresholds already. Ocean circulation patterns are shifting. Ice mass balance has entered net loss regimes. Subglacial hydrology is reorganizing. These are not warnings of future change. They are markers of present transition. Ancient cultures marked such transitions ritually. They acknowledged the end of one era and prepared for another. Modern culture clings to continuity. The reluctance to admit that certain coastlines will not be defended indefinitely mirrors ancient rulers who refuse to abandon cities despite worsening conditions. In both cases, authority becomes tied to denial. Antarctica exposes this tension mercilessly. No political ideology can negotiate with ice physics. No economic incentive can reverse melting already in motion. This is not fatalism, it is realism. Ancient societies that survived collapse did not stop collapse. They navigated it. They relocated populations. They changed subsistence strategies. They restructured social organisation. The lesson is not that collapse is unavoidable, but that transformation is unavoidable. Antarctica's role is not to threaten humanity with extinction. It is to force a choice between managed transition and unmanaged disruption. Technology can still play a role, but only if paired with cultural shifts ancient peoples intuitively embraced. Long-term thinking, distributed resilience, acceptance of limits. Antarctica does not ask for sacrifice out of guilt. It demands adaptation out of necessity. In the next segment, we will examine how Antarctica reshapes global power, not through conquest or conflict, but through geography, and why the most significant political changes of the coming century may be driven by ice rather than ideology. Power has always followed geography, not ideology, not ambition, geography. Empires rise where rivers allow transport. Trade flourishes where coastlines permit access. Security emerges where terrain limits invasion. These patterns have repeated for thousands of years, long before modern politics gave them names. Antarctica is now rewriting geography itself, not by appearing on maps in new ways, but by changing how the rest of the planet functions. As Antarctic ice melts, the redistribution of mass alters Earth's gravitational field slightly but measurably. Satellites already track these changes. Sea levels do not rise uniformly. Some regions experience accelerated flooding, while others see temporary stabilisation. This unevenness reshapes geopolitical reality. Low-lying island nations face existential timelines measured in decades. Delta regions that feed hundreds of millions become increasingly saline. Ports built for 20th century sea levels lose reliability. Shipping routes adapt. Insurance markets retreat. These shifts do not wait for consensus. They move quietly, reshaping incentives beneath the surface. Ancient civilizations experienced similar geographic reconfigurations. When rivers shifted, cities died. When coastlines advanced or retreated, trade networks collapsed or flourished. Power followed adaptation, not dominance. Antarctica acts as a global lever. Its ice loss modifies ocean circulation, especially the Antarctic bottom water formation, a process that drives deep ocean currents worldwide. These currents regulate climate far from the poles, influencing monsoons, storm tracks, and temperature gradients. Disruption here ripples outward. Regions dependent on predictable rainfall may face increasing volatility. Agricultural belts migrate. Populations follow resources. Borders strain. This is not speculation. Models already show these patterns emerging. Ancient societies encoded such shifts into prophecy and cosmology because they lacked spreadsheets. They observed patterns over generations and expressed them symbolically. Modern systems have models, but models do not make decisions. Institutions do, and institutions move slower than ice. There is a tendency to frame climate-driven change as a humanitarian issue. It is that, but it is also a strategic one. Nations that adapt infrastructure early gain stability. Those that resist change face cascading failure. Antarctica does not choose winners. It exposes preparedness. Power in the coming century will not belong to the most technologically advanced nation, but to the most adaptable one. Ancient collapses reveal this repeatedly. Centralized systems failed first. Distributed systems survived longer. The Maya did not vanish overnight. Their urban centres failed when water systems collapsed. Rural populations adapted, migrating and reorganising. The Roman Empire fractured as logistics outpaced governance. Roads remained, authority did not. Antarctica threatens modern logistics more than modern cities. Global trade relies on stable ports, predictable weather windows, and insured risk. As variability increases, trade becomes more expensive. Redundancy replaces efficiency. This is already happening. Shipping insurers adjust premiums based on climate risk. Ports invest in elevation or relocation. Energy grids harden against extreme conditions. These adjustments favour nations with long-term planning cultures. Ancient societies that survived environmental shifts prioritised memory. They recorded floods, droughts and migrations not as isolated events, but as recurring patterns. Modern culture suffers from historical amnesia. We treat each disaster as unprecedented, each crisis as exceptional. This framing prevents systemic response. Antarctica is not an anomaly, it is a phase. Understanding this reframes power not as control, but as resilience. Political systems built around quarterly cycles struggle to address century-scale processes. Yet Antarctica operates on century logic compressed into decades. The mismatch creates instability. The societies that navigate this successfully will not deny change, nor attempt to freeze the world in place. They will redesign systems to move with it. Ancient builders relocated sacred centres when rivers shifted. They reoriented calendars when skies changed. They adapted myth to reality. Modern societies must adapt infrastructure, law and economy to a changing physical baseline. Antarctica forces this reckoning, not through catastrophe alone, but through relentless consistency. Every year, new data confirms trends already visible. The ice does not reverse course. It accelerates or stabilizes, but it does not forget. Memory is Antarctica's lesson. In the next segment, we will look beneath the ice itself, into the landscapes preserved under kilometres of frozen time, and explore why Antarctica is not just a climate archive, but a geological memory vault older than human civilization. Beneath Antarctica's ice lies a world that has not seen sunlight for millions of years, not metaphorically, literally. Radar surveys have mapped entire mountain ranges, river systems, valleys and lakes sealed under kilometres of ice. The Gamburtsev Mountains rival the Alps in scale, yet no human has ever stood on them. Subglacial Lake Vostok has been isolated from the atmosphere for at least 15 million years, possibly far longer. This is not empty space. It is preserved geography, and preservation changes everything. Ice does not simply destroy. In Antarctica, it archives. When continents move, mountains erode. When oceans rise, coastlines vanish. But when ice entombs land, it freezes processes in place. Erosion slows to near zero. Geological time pauses. This makes Antarctica unique on Earth. Other continents overwrite their past constantly. Antarctica keeps it. What scientists are uncovering beneath the ice is not just terrain, but information. Sediment layers record ancient atmospheres. Trapped air bubbles preserve chemical signatures of climates that no longer exist. Isotopes reveal solar cycles, volcanic eruptions, and mass extinctions with precision unmatched anywhere else. Antarctica is Earth's memory core, and memory matters because it allows comparison. Without comparison, change feels unprecedented. With comparison, patterns emerge. Ice cores from Antarctica show that Earth's climate has flipped states rapidly before, sometimes within decades. Temperature jumps of several degrees, abrupt shifts in ocean circulation, sudden collapses of stable systems. The difference now is not the change itself. It is the speed layered on top of human infrastructure. Past transitions occurred when no global civilization depended on stable coastlines, synchronized agriculture, and intercontinental logistics. Today, billions of lives assume climatic continuity. Antarctica reveals that continuity was always an illusion. This realization forces an uncomfortable question. If Earth has undergone rapid destabilizing transitions before, why do we assume our systems are exempt? Ancient societies did not assume exemption. They assumed cycles. Many early calendars were not agricultural schedules alone. They were warning systems. They tracked celestial and environmental rhythms precisely because deviation meant danger. Modern systems track profit and productivity. Environmental deviation is treated as an externality until it becomes catastrophic. Antarctica strips away that denial. Subglacial sediments show periods when Antarctica was green, covered in forests, rivers flowing to the sea, ecosystems thriving. This was not ancient myth. It was the Eocene epoch, roughly 50 million years ago, when global temperatures were only slightly higher than projections for the coming centuries. No ice sheet then, no polar barrier. Sea levels were tens of meters higher. The implication is blunt. Antarctica's ice is not permanent. It is conditional, and conditions are changing. The melting of Antarctic ice is often discussed as a future problem, but satellites gravimetry shows that mass loss is already accelerating, especially in West Antarctica. Ice shelves that buttress inland glaciers are thinning. Once lost, they do not regrow on human timescales. This is not linear melting, it is threshold behaviour. Once certain tipping points are crossed, systems reorganize rapidly. Ancient ice layers show similar thresholds in the past, periods where stability lasted millennia, followed by abrupt collapse. Civilizations built during stable periods flourished. Those that failed to adapt during transitions collapsed. Antarctica's lesson is not doom, it is timing. Adaptation is possible before thresholds are crossed. Afterward, options narrow dramatically. This mirrors patterns seen in ancient collapses. The Indus Valley civilization did not collapse because drought began. It collapsed because urban systems could not reorganize fast enough when monsoon shifted. The Greenland Norse did not vanish because temperatures cooled. They vanished because they refused to adapt culturally while the Inuit did. Antarctica presents the same choice on a planetary scale. Adapt systems or cling to assumptions. There is another layer beneath the ice that complicates the story further: biology. Microbial life has been discovered in subglacial lakes, surviving in complete darkness under immense pressure, isolated for millions of years. These organisms metabolize minerals, not sunlight. They are not relics, they are active. This tells us two things. First, life adapts far beyond conditions humans consider habitable. Second, isolation does not mean stagnation. Antarctica is not frozen in time. It is evolving slowly, quietly, under constraints that force efficiency and resilience. There is an uncomfortable parallel here. Human civilization has optimized for abundance and speed. Antarctic life has optimized for scarcity and endurance. One thrives in stability. The other survives in volatility. As environmental variability increases, which strategy becomes more relevant? Antarctica also preserves records of mass extinctions. Layers corresponding to the Permian extinction, the greatest die-off in Earth's history, are visible in Antarctic sediments. So are markers of asteroid impacts, volcanic megaflares, and ocean anoxia events. The planet has reset before, not once. repeatedly. What is striking is that life always returns, but never in the same configuration. Dominant species disappear, new ones rise, ecosystems reorganize, human civilization assumes continuity of dominance. Antarctica does not support that assumption. It shows that dominance is temporary. Adaptation is permanent. This reframes existential risk. The threat is not extinction of life, but displacement of complexity. Systems simpler than ours may thrive where we fail. Antarctica is a reminder that Earth does not negotiate. It records outcomes, not intentions. The ice does not care whether emissions were accidental or necessary. It responds to physics. And physics is indifferent to politics. Understanding Antarctica is not about fear. It is about realism. It offers a deep time perspective that strips away narratives of exceptionalism. Humans are not the first species to reshape the planet. We are the first to do so knowingly. That knowledge carries responsibility. Ancient cultures encoded environmental memory into myth because they had no other storage medium. Antarctica encodes memory directly into ice and stone. We are now reading it. The question is not whether Antarctica will change. It already is. The question is whether we change fast enough in response. In the next segment, we will examine the legal and geopolitical paradox of Antarctica itself, a continent owned by no one, governed by treaties, and increasingly central to global power, despite its political invisibility. Antarctica is the only continent on Earth without a native human population, without cities, without borders drawn by war or empire. And yet it may be the most politically fragile place on the planet. On paper, Antarctica is protected. The Antarctic Treaty System, signed in 1959, declares the continent a scientific preserve. No military activity, no nuclear testing, no mineral extraction, no sovereignty claims enforced. It sounds ideal. It is also temporary. The treaty does not eliminate national interests. It suspends them. 7 countries maintain territorial claims they have not withdrawn, only frozen. Others, including global superpowers, reserve the right to make claims in the future. Scientific research stations double as geopolitical footholds. Logistics infrastructure quietly establishes presence. Antarctica is neutral only as long as conditions remain stable. History shows what happens when stability ends. Every time a resource becomes critical, neutrality collapses. Whales once seemed infinite. They were protected until oil demand rose. Then whaling exploded despite treaties. Cod stocks were managed until economic pressure overrode science. Freshwater aquifers are protected until drought turns them into leverage. Antarctica contains 70% of the world's fresh water locked in ice. As water scarcity increases globally, that statistic stops being academic. Melting ice does not just raise sea levels, it releases fresh water into the Southern Ocean, altering global circulation patterns. But politically, it also reframes Antarctica from remote to relevant. Relevance attracts power. New shipping routes through the Southern Ocean are becoming more viable as ice conditions change. Rare earth elements and mineral deposits, currently protected by treaty, are increasingly mapped using satellite surveys. Biological compounds discovered in extremophile organisms attract pharmaceutical interest. The treaty bans extraction, not curiosity. Curiosity becomes pressure. Pressure becomes justification. Already, treaty reviews occur at scheduled intervals. Each review reflects current global priorities more than original ideals. Environmental protection remains dominant for now, but treaties are only as strong as the cost of breaking them. If future crises make Antarctic resources essential to national survival, ethical language will bend. This is not cynicism, it is historical pattern recognition. Empires do not expand because they are evil. They expand because constraints loosen. Antarctica's constraint is ice. As ice retreats, ambiguity grows. There is another subtler geopolitical issue: data control. Scientific research in Antarctica generates immense data sets. Climate records, atmospheric chemistry, subglacial mapping, biological samples. Who owns this data? Who interprets it? Who decides which findings are emphasised or delayed? Information shapes policy. Policy shapes response. Response shapes survival. Antarctica is not just a physical space. It is an epistemic one. The continent influences global climate models that inform trillions of dollars in infrastructure decisions, seawall investments, agricultural planning, disaster preparedness. If those models underestimate Antarctic instability, societies overcommit to assumptions that fail. If they overestimate it, resources may be misallocated. Accuracy matters. Yet Antarctica's remoteness makes verification slow and expensive. Most nations rely on shared datasets they did not collect themselves. Trust becomes a factor. In geopolitics, trust is fragile. This fragility extends to science itself. Antarctic research is slow by necessity. Field seasons are short. Conditions are brutal. Equipment failures are common. Data gaps persist. Meanwhile, policy decisions move faster. This mismatch creates tension. Slow truth versus fast action. Historically, civilizations that failed to align decision speed with environmental feedback suffered. The Maya tracked climate precisely, but political fragmentation prevented coordinated response. Roman engineers understood infrastructure limits, but expansion continued until maintenance collapsed. Antarctica warns against the same error at a planetary scale. There is also a psychological distance problem. Antarctica feels abstract. Few people will ever see it. Media images show white emptiness, not dynamic systems. Melting ice lacks the immediacy of burning forests or flooded streets. Distance breeds delay. Delay amplifies risk. Ancient cultures feared the poles, not because they understood ice physics, but because they associated them with balance points of the world, places where small disturbances had large consequences. Modern science confirms that intuition. The Antarctic ice sheet interacts with ocean currents that regulate global temperatures. Disturbances there propagate worldwide. This means decisions made far from Antarctica, energy policy, land use, emissions, feedback into polar stability. Antarctica is passive only in appearance. It responds with lag, not indifference. Lag is dangerous because it disguises momentum. By the time effects are obvious, processes are already committed. This is why Antarctica is central to the concept of irreversibility. Some changes can be reversed, infrastructure rebuilt, economies restructured, policies rewritten. Ice sheet collapse cannot. Once certain thresholds are crossed, regrowth takes thousands of years. Civilizations plan in decades. Ice operates in millennia. That mismatch creates blind spots. Antarctica forces confrontation with deep time, a scale humans struggle to emotionally grasp. And emotion matters because action requires motivation. Data alone does not move societies. Narratives do. Antarctica's narrative is still forming. Is it a warning, a resource, a laboratory, a battleground, a relic? The answer depends on choices made now. In the next segment, we will explore how Antarctic research has repeatedly overturned scientific certainty, how discoveries beneath the ice forced revisions of what we thought we knew about Earth's stability, resilience, and limits. For decades, Antarctica was treated as the most stable part of the planet. Cold meant frozen. Frozen meant static. Static meant safe. That assumption was wrong. And the reason it survived for so long is uncomfortable. Antarctica is hard to measure. expensive to access, and slow to contradict theory. Early climate models treated the Antarctic ice sheet as inert background mass. It was a boundary condition, not a variable. Models focused on the Arctic because it melts faster, affects shipping, and sits near population centres. Antarctica was assumed to respond slowly enough that humans could adapt. That belief collapsed piece by piece. The first cracks came from the ice core data. Deep drilling projects revealed that Antarctic climate had flipped abruptly in the past. Temperature jumps of several degrees within decades, not millennia. These were not smooth transitions, they were thresholds. Then came satellite gravity measurements. NASA's GRACE satellites detected mass loss, patterns that ground teams had missed. Entire ice basins were thinning from below, not above. Warm ocean water was infiltrating beneath ice shelves, melting them invisibly. This mattered because ice shelves are not ice sheets. They are braces. Remove the brace, and the structure behind it accelerates. That acceleration was not linear, it was exponential. One of the most destabilizing discoveries was marine ice sheet instability. Large portions of Antarctica rest on bedrock below sea level, sloping downward inland. Once retreat begins, it self-reinforces. This means there is no stable midpoint. Either the ice holds or it doesn't. Models had not accounted for this adequately. When they did, projected sea level rise doubled in some scenarios, then tripled. And still, uncertainty remained high. Uncertainty does not mean ignorance. It means the system is sensitive. Sensitive systems punish delay. Another assumption failed next. Biological inactivity. Antarctica was thought to be biologically sparse, with life confined to margins. Instead, scientists discovered vast subglacial ecosystems, microbial communities, surviving under kilometres of ice, metabolizing minerals, producing gases, altering chemistry. Life was not just present, it was active. This matters because biology interacts with physics. Microbes affect methane cycles. Chemical reactions affect ice lubrication. Lubrication affects flow speed, again, feedback loops. Each discovery forced model revisions. Each revision increased risk ranges rather than narrowing them. This is a red flag in system science. When uncertainty expands with better data, the system is more volatile than expected. Antarctica stopped being a slow variable. It became a potential trigger, and triggers do not announce themselves clearly. They accumulate quietly until they fire. Another overlooked factor, seismic activity. Antarctica sits on a geologically active crust. Subglacial volcanism had been acknowledged but minimized. Recent radar mapping revealed hundreds of volcanic structures beneath the West Antarctic ice sheet. Not erupting, but warm. Heat flux from below weakens ice from the base. Combined with ocean warming from the sides, ice is attacked from all directions. This is not catastrophic in isolation. It becomes catastrophic in combination. Complex systems fail when multiple stressors synchronize. The lesson here is blunt. Antarctica is not a frozen monument. It is a dynamic system approaching states we have never observed directly. Humanity is running an experiment without a control group, and the experiment is not reversible. What makes this more dangerous is institutional inertia. Scientific consensus moves cautiously by design. Policy moves even slower. Meanwhile, physical processes do not negotiate. By the time a scientific finding is robust enough to be politically actionable, the system may already be committed. This gap between knowledge and action is where collapse hides. Antarctica has exposed this gap repeatedly. Each major discovery, rapid basal melting, grounding line retreat, ice shelf hydrofracture, was initially controversial, then accepted, then outdated by the next finding. The pace of revision is accelerating. Acceleration is the opposite of stability. There is a deeper implication that rarely gets stated plainly. Human governance is structurally mismatched to planetary systems. We govern through borders. Antarctica ignores borders. We plan through budgets. Ice responds to energy imbalance. We act through elections. Glaciers respond to cumulative forcing. No treaty, no matter how idealistic, can override physics. The Antarctic Treaty assumes that nations will continue to value restraint over desperation. That assumption has never held indefinitely anywhere else. The continent is not just testing climate models, it is testing political ones. Can cooperation survive stress? Can long-term risk outweigh short-term advantage? Can absence of ownership prevent competition? History suggests pessimism is rational, but pessimism alone is useless. The point of understanding Antarctica is not fear, it is calibration. If Antarctica collapses faster than expected, coastal infrastructure planning fails. If it remains stable longer, misallocated resources could undermine resilience elsewhere. Either error is costly. Antarctica forces precision, and precision requires honesty. Honesty about uncertainty, honesty about incentives, honesty about limits. In the next segment, we will examine the Antarctic Treaty itself, how it works, where it is strong, where it is fragile, and why its greatest vulnerability is not violation, but reinterpretation. Before systems collapse, they usually appear stable. That is one of the most dangerous illusions in complex environments. Antarctica today feels orderly because nothing dramatic is happening there yet. Research stations operate on schedules. Scientists rotate in and out. Ice still dominates the landscape. Maps still look familiar, but stability in complex systems is not maintained by balance. It is maintained by buffers, and Antarctica's buffers are thinning. In climate science, tipping points are moments when gradual change becomes sudden transformation. Ice sheets do not melt evenly. They weaken internally until structural failure cascades. One section collapses, destabilizing others. What took centuries to build disappears in decades or years. Governance systems behave the same way. The Antarctic Treaty System relies on buffers that are quietly eroding. High logistical cost, limited accessibility, low commercial incentive, slow environmental change. Remove enough of these and behaviour changes abruptly. This is where most people make a mistake. They imagine a future where nations openly announce territorial grabs or mining operations. That is not how breakdown happens. Breakdown happens through exceptions, emergency permissions, temporary waivers, special research exemptions, humanitarian interventions, security assistance, each one justified, each one narrow, each one precedented. Once precedent exists, the system shifts. Consider this scenario, not speculative, but structurally plausible. A large research vessel carrying tourists strikes ice, weakened by warming waters. The hull is breached. Hundreds of civilians are at risk. Weather conditions prevent immediate evacuation. A nearby nation deploys military-grade icebreakers and aircraft to assist. Personnel establish temporary command infrastructure. Supplies are staged. Communication systems are installed. The rescue succeeds. No one objects. Why would they? Lives were saved. But the infrastructure remains for months to support ongoing recovery operations. Then for a year, because dismantling it is costly. Then it becomes dual-use scientific support. The treaty was not violated, but the norm was altered. Now imagine this happens twice, then 3 times, then with multiple nations. At some point, Antarctica is no longer demilitarized in practice, only in language. This is how institutional tipping points occur. They do not announce themselves. They normalize themselves. Another pressure point lies in data. Antarctica is one of the most valuable climate monitoring locations on Earth. ice cores, atmospheric measurements, subglacial mapping. These are not just scientific assets, they are strategic ones. Who controls data controls narratives. As climate impacts intensify, nations will want preferential access to predictive models. Early warning of sea level rise or resource shifts becomes economically valuable. Data exclusivity becomes power. Scientific collaboration assumes openness. Geopolitics assumes leverage. These assumptions cannot coexist indefinitely. Already, some research data is restricted under national security classifications. This trend will expand, not contract. When knowledge becomes strategic, transparency declines. Another underestimated tipping factor is technology substitution. Historically, Antarctica was protected by human limits. Cold-killed, distance exhausted, isolation enforced caution. Autonomous systems change this completely. Uncrewed drones can operate continuously. Robotic drills can penetrate ice without human presence. Remote sensing can map subglacial structures in real time. The moment humans are no longer required on site, oversight weakens. Inspection regimes rely on visiting stations. If stations are automated, what is inspected? Technology decouples activity from visibility. This is not inherently malicious, but it is destabilizing. The treaty was written for humans, not machines. There is also a cultural tipping point. Antarctica has been framed as belonging to no one, which subtly means belonging to everyone. But shared ownership without enforcement often leads to overuse. This is the classic tragedy of the commons, but on a planetary scale. As climate anxiety grows, Antarctica becomes symbolically loaded. Some see it as humanity's last untouched refuge. Others see it as an unfairly locked resource in a desperate world. Narratives diverge. Once moral framing splits, consensus becomes harder. And consensus is the treaty's backbone. The most dangerous moment for any system is when it transitions from inconvenient to challenge. As long as Antarctica is merely expensive, restraint holds. Once it is seen as strategically necessary, restraint erodes. We are closer to that transition than most people realise. Sea level projections are tightening. Freshwater scarcity is accelerating. Critical minerals are geopolitically concentrated. Antarctica sits at the intersection of all three. The treaty delays conflict, but it does not eliminate pressure. Pressure accumulates silently. In the next segment, we need to confront a harder question, one most discussions avoid entirely. What if Antarctica is not just environmentally fragile, but historically non-empty in ways we are unprepared to contextualize? What if beneath the ice are not just geological formations, but anomalies that complicate governance, ownership, and even narrative control? Antarctica has always benefited from one powerful assumption, that nothing of consequence lies beneath it except ice and rock. That assumption has acted as a psychological stabilizer. It makes restraint easier. It keeps curiosity academic instead of urgent. It allows nations to tell themselves that Antarctica is valuable mainly as a warning system for climate, not as a place that could change history. But that assumption is weakening, not because of conspiracy and not because of fantasy, but because of data. Over the last 2 decades, radar, gravimetric surveys and seismic imaging have revealed a continent that is far from uniform beneath the ice, subglacial lakes the size of cities, mountain ranges larger than the Alps, vast sedimentary basins shaped by ancient water systems, heat, anomalies inconsistent with simple tectonic models. None of this implies lost civilizations or hidden technology, but it does imply a past that is far more complex than we once believed. And complexity creates governance problems, because the moment Antarctica stops being empty, It stops being neutral. Subglacial Lake Vostok is a good example, not because it hides anything extraordinary, but because of how it changed behaviour. When scientists realised there was a lake sealed under kilometres of ice for millions of years, the rhetoric shifted instantly. No longer was the question, should we drill? It became, how fast can we drill without contamination? Curiosity overrode restraint. That same pattern is emerging again, this time with subglacial geology. New surveys show sediment layers that imply long-standing liquid water environments, not just transient melting, but sustained systems capable of preserving biological, chemical and geological records from deep time. These records are not just academic. They could rewrite climate models. They could refine sea level projections. They could reshape our understanding of Earth's resilience and fragility. And whoever controls that information gains disproportionate influence over global policy narratives. This is where science and power quietly collide. Scientific discoveries do not remain neutral when their implications affect economies, borders, and survival planning. Data becomes leverage. Imagine two futures. In the first, Antarctic subglacial. Data shows that ice sheet collapse is likely slower than feared. Coastal investments continue. Governments delay expensive adaptation measures. In the second, the data shows faster, non-linear collapse pathways. Entire regions become uninsurable. Migration planning accelerates. Political instability rises. Which governments want early access to that information? Which want exclusive interpretation rights? Which want time to act before others even know the scale of the threat? This is not hypothetical. It is how information has always been treated when stakes are high. Antarctica's data is no longer passive science, it is strategic forecasting. And that shifts incentives. Another overlooked dimension is legal latency. International law evolves slowly. Technology evolves quickly. When the two diverge, grey zones appear, and grey zones are exploited. The Antarctic Treaty bans military activity, but allows military personnel for peaceful purposes. It bans resource extraction, but allows scientific sampling. It prohibits sovereignty claims, but does not prohibit influence accumulation. These distinctions were clear in 1959. They are porous in 2026. Autonomous systems blur military versus civilian. Dual-use infrastructure blurs science versus logistics. Data dominance blurs collaboration versus control. Legal language struggles to keep up. Now add one more destabilizing factor: time pressure. The treaty works because it assumes patience. Climate reality does not. As ice destabilization accelerates, research timelines compress. Decisions that once took decades are now made in years. Funding cycles shorten. Risk tolerance rises. Urgency erodes caution. This is precisely when systems break, not from malice, but from necessity. History shows this pattern repeatedly. Treaties hold until circumstances make compliance feel irresponsible. At that point, actors justify deviation as pragmatism rather than betrayal. Antarctica is approaching that inflection point, but there is a deeper layer that most public discussions avoid, because it is uncomfortable, not speculative, but epistemically disruptive. Antarctica is one of the least archaeologically explored landmasses on Earth. Not because there is evidence of ruins, but because conditions prevent confirmation either way. Ice preserves exceptionally well. Ice also hides completely. If anomalies were discovered, structures, artifacts, or even unexplainable formations, the consequences would be immediate and profound, not because they prove anything extraordinary, but because they break neutrality. Who excavates? Who verifies? Who controls disclosure? Who owns interpretation? Even natural anomalies create political earthquakes. Imagine the discovery of mineral formations critical to future energy technologies, or biological ecosystems with pharmaceutical potential, or geological evidence that forces a revision of human migration timelines, Antarctica cannot absorb such discoveries quietly. The treaty was designed to prevent conflict over known resources. It was not designed to handle paradigm-shifting unknowns. This is why secrecy becomes tempting, not because of malice, but because disclosure creates instability. If one nation believes another has found something transformative, trust collapses, inspection regimes intensify, accusations rise, cooperation fractures, transparency is virtuous, until it becomes dangerous. This paradox sits at the heart of Antarctica's future. The continent is stable because we agree to treat it as unimportant beyond science. The moment it becomes important, agreement falters. And importance is no longer theoretical. Climate stress is making Antarctica relevant in ways it never was before. The irony is brutal. We protected Antarctica by ignoring it. We are now forced to study it because ignoring it may doom us. This tension will not resolve cleanly. In the next segment, we need to examine a question that follows naturally from this pressure. If Antarctica is entering a phase of unavoidable relevance, what mechanisms exist to prevent it from becoming the next geopolitical fault line, and are they sufficient? Antarctica was never designed to handle relevance. That is the core problem. The systems governing the continent were built on an assumption that has quietly expired, that Antarctica would remain peripheral to human survival and power dynamics. As long as it was cold, distant, and seemingly empty, cooperation was easy. Cooperation thrives where stakes are low. But relevance changes behaviour faster than ideology ever could. The Antarctic Treaty system was revolutionary for its time, but it was also a product of a very specific historical moment. Post-World War II exhaustion, nuclear fear, a rare alignment where restraint felt safer than ambition. The treaty froze sovereignty claims, prohibited military activity, and elevated science as the primary justification for presence. What it did not do was anticipate strategic science. Science today is not just discovery, it is prediction, leverage, and timing. When radar penetrates ice, it doesn't just reveal geology, it reveals future coastlines. When ice core analysis refines climate sensitivity, it doesn't just advance models, it reshapes insurance markets and national budgets. When subglacial heat flow is mapped, it doesn't just explain melting, it informs infrastructure survival timelines. In other words, Antarctic science now tells nations who loses land first, who must relocate populations first, and who bears economic collapse first. That makes it power, and power changes incentives. The treaty's enforcement mechanisms were never designed for asymmetric information. They rely on mutual inspection, voluntary transparency, and trust that scientific findings will be shared openly. But when information determines national survival, transparency becomes conditional. This is not a moral judgment. It is a systemic reality. We have seen this before. Nuclear physics was once an open academic field. Then its implications became clear, and secrecy followed immediately. Climate modelling itself underwent similar shifts, with certain projections restricted, delayed, or politically filtered. Antarctica is following that trajectory now. The infrastructure on the continent reflects this shift. New research stations are larger, more permanent, more technologically advanced. Runways are being extended. Power systems are being hardened. Satellite uplinks are increasing in bandwidth and redundancy. Officially, this is about efficiency and safety. Unofficially, it reflects long-term commitment. No nation invests that heavily in something it plans to abandon. The phrase peaceful scientific presence begins to blur when logistics resemble permanence, and permanence invites influence. Influence invites competition. Competition invites rationalization. This is how neutral spaces erode, not through sudden violation, but through gradual reinterpretation. Another pressure point is inspection asymmetry. While the treaty allows inspections, they are not continuous. They are scheduled. They are limited. They rely on cooperation. But modern research generates enormous volumes of data. Raw radar scans, seismic readings, AI-processed models that cannot be meaningfully inspected by walking through a station. You can inspect buildings. You cannot inspect algorithms. If two stations collect the same data but interpret it differently, there is no enforcement mechanism to determine intent or bias. This creates a structural vulnerability. The treaty assumes honesty. Modern geopolitics assumes advantage. That mismatch is widening. Now consider the role of private actors. Antarctica is governed by states, but science increasingly relies on private technology. Satellite companies, AI modelling firms, advanced materials suppliers, logistics contractors. These entities are not bound by the treaty in the same way governments are. Data ownership becomes murky. Accountability becomes fragmented. Motives diversify. A private firm analysing Antarctic ice data may legally share insights with clients who have no treaty obligations at all. This is not illegal. It is simply unanticipated. And unanticipated dynamics are where systems fail. There is also a psychological dimension rarely discussed: symbolic precedent. Antarctica is humanity's last large-scale experiment in restraint. If cooperation collapses there, quietly, incrementally, it sends a signal far beyond the ice. It tells the world that no space remains immune to competition once stakes rise high enough. That signal matters because the next frontiers, deep ocean, orbital infrastructure, lunar resources, are watching. How Antarctica is handled will shape how all future shared domains are treated. If secrecy and competition dominate, cooperation elsewhere becomes performative. This is why Antarctica is not just about ice. It is about whether global governance can function under stress. There is one more destabilizing factor that must be addressed, because ignoring it creates blind spots: uncertainty itself. The most dangerous discoveries are not the dramatic ones, but the ambiguous ones. If data suggests anomalies that are not easily explained, unusual heat flow patterns, structures that could be natural or something else, signals that defy existing models, then decision makers face a dilemma: announce uncertainty and risk misinterpretation, suppress uncertainty and risk exposure later. Either choice has consequences. This is where institutional caution often crosses into opacity, not because something is being hidden, but because no one wants to be responsible for destabilizing narratives. History shows that paradigm shifts are rarely welcomed in real time. They are resisted, delayed, and reframed until they become unavoidable. Antarctica may already be in that phase, not because something extraordinary has been found, but because what might be found is now significant enough to alter behaviour. The possibility alone changes the game. This brings us to the uncomfortable question most discussions avoid. Is the Antarctic Treaty still capable of handling a future where Antarctica matters economically, strategically, and existentially? Or is it structurally destined to fracture under that weight? In the next segment, we'll examine historical precedents where treaties faced similar stress, and what actually happened when ideals collided with survival. At this point in the story, it feels tempting to believe we understand what happened. The gods arrived, they ruled, they withdrew, and humanity was left behind to grow on its own. That sequence feels clean, almost reassuring. It suggests a beginning, a middle, and an end. But that neatness is the first thing that deserves suspicion, because the ancient world did not describe withdrawal the way we imagine departure. They did not describe gates closing. They did not describe silence. They did not describe absence. They described change in behaviour, and that difference matters. Across Sumerian, Akkadian, and early Babylonian texts, the language does not say the gods were gone. It says they were no longer seen, no longer approached, no longer addressed directly. That distinction is subtle, but critical. In administrative records from the late Sumerian period, offerings do not stop. They change in frequency, ritual. Calendars do not vanish. They compress. Priestly roles are not eliminated. They become specialized, restricted, and hereditary. This is not how cultures behave when a power disappears. This is how cultures behave when access is limited. There is also something else the tablets never say. They never say the world is safer afterward. In fact, the opposite is implied. After the so-called withdrawal, texts become obsessed with thresholds, purity rules, forbidden zones, and timing constraints. More rules appear, not fewer. More warnings, not fewer. If divine oversight had truly ended, one would expect a loosening of ritual control. Instead, the system tightens. That suggests not abandonment, but containment. The Anunnaki are no longer public-facing, but they are not erased from operational reality. Their presence shifts from visible authority to background constraint. Like infrastructure, you do not see power lines buried beneath a city, but everything stops if they fail. This is where the narrative becomes uncomfortable, because the assumption that humanity was left alone may not be accurate. What may have happened instead is that humanity was placed inside a closed system, a system designed to run without constant supervision, but still bounded by rules established earlier. The ancient texts hint at this repeatedly, but never explicitly. They speak of fixed destinies, of appointed times, of paths that may not be crossed. These are not metaphysical abstractions. They are operational constraints, and constraints only matter when something remains active enough to enforce them. Consider the temple closures again. They were not destroyed, they were sealed. Sealing is not abandonment. Sealing is preservation. In multiple sites, doorways were blocked in ways that prevent casual entry but allow reopening. Drainage systems were protected. Sacred objects were arranged deliberately, not discarded. This is the behaviour of a culture preparing for long dormancy, not permanent loss. The texts describing the departure ceremony emphasise continuity more than finality. Words equivalent to until, appointed, and cycle appear more often than words meaning end. This is not poetic accident. Sumerian scribes were bureaucrats. When they meant permanent, they said permanent. Here they did not. Another detail often overlooked is how human leadership changes after this period. Kings no longer claim direct conversation with gods. Instead, they claim dreams, signs, omens. This shift is usually interpreted as decline, but from another angle, it looks like a change in interface. Direct command is replaced by indirect signalling. That is exactly how complex systems scale. When a system becomes too large or unstable for constant intervention, you don't remove control. You automate it. Rules replace oversight. Signals replace speech. Thresholds replace judgment. From that perspective, the Anunnaki did not leave humanity to its own devices. They left humanity inside a framework designed to test something, not obedience, but stability. The flood narratives support this reading. They are not framed as punishment alone. They are framed as evaluation. Who survives? Who rebuilds? Who remembers instructions? And crucially, who does not attempt to summon direct intervention again? After the flood, contact becomes conditional, mediated, rare, encoded. This is consistent with a system entering monitoring mode rather than active control. Think of the language used for the remaining watchers. They are not rulers. They are not governors. They are described as those who observe, measure, record. This is not mythology drifting into fantasy. This is administration drifting into background process, which raises a disturbing possibility. If the Anunnaki withdrawal was not a departure, but a transition to low interference oversight, then humanity has never truly been outside the system. It has been inside an experiment, mistaken for independence. That interpretation reframes everything that follows: the rise and fall of civilizations, the repetition of collapse, the strangely consistent ceilings civilizations hit before destabilizing. These patterns stop looking like failure. They start looking like boundary testing. Every time humanity centralizes too much power, something breaks. Every time it accelerates beyond control, instability follows. Every time it approaches irreversible harm, intervention appears, sometimes subtle, sometimes catastrophic, not as judgment, as correction. The ancient world lacked language for this idea, so it used gods. But the behaviour described is not divine temperament, it is system regulation. And systems do not care about belief. They care about thresholds, which leads to a question the ancient texts never asked directly, but circle relentlessly. What exactly was humanity being tested for? Not worship, not loyalty. Those end once direct. Presence ends. What remains is something more dangerous: self-governance under constraint, the ability to grow without destroying the environment that sustains growth, the ability to wield power without triggering collapse, the ability to remember limits without enforcement. Seen this way, the Anunnaki departure becomes the start of the real trial, not the end of divine involvement. A test designed to run for thousands of years, with watchers, not rulers, signals, not commands, consequences, not warnings. And if that is true, then the most important events in human history may not be beginnings or endings at all. They may be diagnostics, moments when the system checks whether humanity is approaching a boundary it cannot recover from, and adjusts accordingly. If that idea unsettles you, it should, because it means history is not a record of freedom gained. It may be a record of containment maintained, and containment only matters if something powerful enough still exists to enforce it. Which brings us to the question this segment quietly prepares the listener for: if the Anunnaki never fully left, then what exactly are the cycles we keep detecting? And why do they seem to activate when humanity reaches the same dangerous thresholds again and again? Once you stop treating the ancient world as myth and start treating it as a record of system behaviour, something unsettling appears. The collapses are not random, they are patterned, and more importantly, they are selective. When civilizations fall, not everything is destroyed, not even close. Languages fracture, but symbols survive. Cities drown, but specific sites remain untouched. Technologies vanish, but foundational principles resurface later, intact. That is not how blind catastrophe behaves. Floods do not spare observatories. Earthquakes do not selectively preserve knowledge centres. Ice ages do not seal archives while erasing surrounding settlements. Yet again and again, that is exactly what the record shows. Consider where the deepest preservation occurs, not in royal palaces, not in population centres, but beneath temples, beneath ritual complexes, beneath sites associated with timing, measurement, and observation. This matters. If a civilization collapses naturally, its most fragile systems fail first. Knowledge disperses chaotically, records scatter or rot. But when collapse follows a pattern where core informational structures are protected, Something else is happening. Someone anticipated collapse and prepared for it. This is where the idea of purely natural cycles breaks down. Yes, climate shifts occur. Yes, floods happen. Yes, impacts, eruptions, and freezes shape history. But natural forces do not design knowledge survivability strategies. Intelligence does. Across multiple eras, we see civilizations reaching a peak of complexity and then undergoing a sharp contraction that preserves specific things while eliminating others. Population density collapses. Political systems dissolve. Large-scale industry halts, but calendars persist. Astronomical alignments remain correct. Sacred geometries survive intact. It's as if the system trims excess while preserving core variables, like pruning. And pruning is not destruction, it is maintenance. This reframes the idea of the reset. The resets are not wipes, they are reductions, not designed to erase humanity, but to bring it back within tolerable parameters. Which parameters? The ancient texts never state them explicitly, but the symptoms suggest three: environmental overreach, technological imbalance, social instability beyond recovery. Every major collapse correlates with at least two of these, sometimes all three, and in each case, the collapse arrives faster than natural degradation alone would predict. That acceleration is key. Slow decline does not produce myths of sudden darkness, boiling seas or skyfire. Rapid correction does. What ancient people described as divine wrath looks through a modern lens like threshold-triggered intervention. Not emotional, not moral, operational. And that idea becomes more disturbing when we examine what doesn't happen after collapses. Humanity does not return to zero, it returns to baseline. Stone tools reappear, but not randomly. Agriculture returns almost immediately. Social organisation reforms too quickly to be purely rediscovered. These are not fresh starts, they are recoveries, as if some knowledge was never lost, only withheld from widespread use. Which brings us to the strangest continuity of all, the role of specialists. After every collapse, certain individuals emerge almost immediately. They understand timing, they understand land cycles, they understand stars. They do not claim innovation, they claim inheritance. Shamans, sages, keepers, watchers, different names, same function. They act as stabilizers, they limit expansion, they ritualize restraint, they encode knowledge into myth and taboo. Why encode? Because open systems destabilize faster. Knowledge distributed without constraint accelerates growth, and growth triggers collapse. So knowledge is disguised, wrapped in religion, bound by ritual, restricted by initiation, not because it is false, but because it is dangerous when unbounded. This is why advanced concepts often appear first in sacred contexts: geometry hidden in temples, astronomy embedded in myth, engineering disguised as ritual. These are not primitive misunderstandings, they are safeguards, and this pattern continues until something changes. Writing. Once writing becomes widespread, knowledge preservation changes shape. Information no longer relies solely on memory and ritual. It becomes externalized, and that is when the system begins to fail more often. Because writing breaks containment. Texts can be copied. Ideas spread faster than cultural adaptation. Technological knowledge escapes its ritual gatekeepers. The result? Civilizations begin overshooting, limits more rapidly, and collapses become harsher. This escalation pattern is visible. Early collapses are regional, later ones are continental. Eventually they become global, which suggests the system is struggling to compensate for humanity's increasing speed. This is not the behaviour of a passive universe. It is the behaviour of a stressed control architecture. And here is where the ancient watchers become relevant again. They are not there to rule. They are there to monitor rate of change. Rate matters more than state. A slow-growing civilization can be guided. A rapidly accelerating one destabilizes before correction can be gentle. This explains why myths emphasize warnings ignored, not sins committed. Warnings ignored. Warnings are signals. Signals imply monitoring. Monitoring implies presence, which brings us back to the lie hidden in plain sight. The idea that the Anunnaki left because humanity no longer needed them, that story comforts us. But the evidence suggests something colder. They withdrew because direct intervention was no longer sustainable. Not because the experiment ended, but because it entered a phase where overt control would contaminate the results. In other words, humanity was not abandoned. Humanity was released into unsupervised operation, with safeguards still in place. Like a system switched from manual control to automated thresholds. An automation is ruthless. It does not negotiate. It does not warn twice. It does not explain. It corrects. This reframes every myth of destruction as a log entry. Every flood, every darkness, every fire from the sky, not as punishment, but as system response. And now we reach the part most people instinctively resist. If that system still exists, then it is not ancient history, it is present tense, because automated systems do not shut off just because operators leave. They persist until disabled. And nothing in the ancient record ever describes the system being dismantled, only stepped away from, which leads to an unavoidable question. If the resets are responses to thresholds, then what thresholds are being approached now? And more importantly, has the system already begun to react? Good. Then we don't soften it, we narrow it. Because once you accept that the collapses follow threshold behaviour, the question stops being what happened and becomes how close are we now? And the answer is uncomfortable. Every civilization before ours triggered collapse. By crossing limits it didn't recognise until too late. But none of them shared one trait we now take for granted: global synchronization. Ancient societies were fragmented. Even the most expansive empires operated at regional scales. Information moved slowly. Innovation diffused unevenly. Collapse, when it came, was buffered by distance and delay. Ours is different. We crossed the synchronization threshold sometime in the last century. Energy grids interlinked continents. Financial systems fused into a single feedback loop. Communication collapsed distance into seconds. Supply chains became globally interdependent. This created a new condition the ancient system never had to manage before: a single point of failure civilization. In earlier cycles, collapse could be localized. A region failed, others adapted. Knowledge survived in parallel cultures. Recovery pathways existed. Now, failure propagates. A disruption in one domain cascades instantly into others. Economic instability triggers political unrest. Political unrest disrupts infrastructure. Infrastructure failure destabilizes food systems. Food insecurity amplifies conflict. This is not hypothetical. It is already observable. Which means, if the system responds to rate of destabilization, not morality or intent, then modern humanity is not approaching a collapse threshold slowly. It is sprinting toward it. And this is where ancient records stop being metaphor and start behaving like diagnostics. Flood myths emphasize rapid sea rise, not gradual encroachment. Fire myths emphasize sudden ignition, not long-term warming. Darkness myths emphasize particulate blocking light, not simple nightfall. These are not poetic exaggerations. They are descriptions of non-linear events. Events triggered when systems overshoot stability margins. The ancients didn't know equations, but they understood consequence. And they understood timing. which is why so much effort went into calendars, cycles, and long duration counting, because prediction mattered more than explanation. If you know when a threshold approaches, you can prepare. And preparation does not mean prevention, it means survivability. This is where the idea of chosen survivors gets twisted in modern retellings. It was never about worth, it was about function. Survivors were not selected for purity or virtue. They were selected for information retention. The people who survived resets carried agricultural knowledge, seasonal awareness, construction, principles, navigation frameworks, not weapons, not empires, not ideology, because post-collapse environments do not reward dominance, they reward adaptability. This is why survivors are almost always described as builders, farmers, healers, and observers, never conquerors. And this brings us to the most dangerous modern misunderstanding: the belief that technological advancement automatically increases survivability. It doesn't. It often does the opposite. High complexity systems collapse harder. The more layers are required to sustain daily life, the more brittle the civilization becomes. Ancient societies knew this instinctively. They limited scale through ritual. They capped growth through taboo. They enforced pauses through festival cycles. These weren't superstitions. They were governors. Our civilization removed them. Efficiency replaced restraint. Speed replaced reflection. Growth replaced balance. And now the feedback loops run unchecked, which again raises the same question. Ancient watchers asked, can this system self-regulate fast enough to avoid correction? There is no moral judgment embedded in that question, only mechanics. And mechanics don't care about intention. This is why the idea of a future intervention feels both terrifying and oddly familiar, because if the system still operates, intervention would not look like gods descending in fire. It would look like constraints activating, environmental constraints, energetic constraints, biological constraints, not targeted punishment, system-wide limitation. And here is where modern science begins, brushing against ancient narrative, planetary boundaries, tipping points, runaway feedback loops, different language, same warning. The difference is ancient cultures framed it as memory. We frame it as prediction. But prediction without humility becomes arrogance, which brings us to the final inversion that most people miss. If earlier civilizations fell because they exceeded limits, and if we are approaching those same limits faster than ever, then the true legacy of the seventh civilization is not dominance, it is choice. For the first time, humanity can see the cycle clearly, not through myth, through data. We can recognize thresholds, model consequences, intentionally slow growth. No civilization before us had that option. They felt the system only when it struck. We can feel it before it activates. That changes everything, unless we ignore it. And history suggests that intelligence does not guarantee wisdom. So the question left hanging is not whether another reset is possible. It is whether awareness alone is enough to prevent it, or whether the system was never designed to be overridden, only endured. Then we stop pretending this is abstract, because the moment you accept that collapse follows observable thresholds, another possibility becomes impossible to ignore. What if the system isn't blind, not conscious in the human sense, not emotional, but monitored? Every advanced system ever built by humans includes oversight, feedback, measurement, intervention triggers. We don't design aircraft, reactors, or networks to operate without diagnostics. Yet we assume that a planetary system capable of resetting civilization repeatedly does so without any form of observation. That assumption is lazy. Ancient texts never describe the watchers as rulers forever. They describe them as stewards, record keepers, measurers of time, and most importantly, withdrawers. Withdrawal is not disappearance, it is distance. Distance allows observation without interference, and interference, according to every ancient source that bothers to explain motive, was the problem. Too much guidance prevented adaptation. Too much correction weakened resilience. So they stepped back, not because humanity was finished, but because humanity needed to be tested without support. This reframes the entire idea of gods, visitors, or overseers. They weren't benevolent saviours. They weren't tyrants. They were systems engineers managing an experiment with planetary scale. And experiments have phases: initialization, acceleration, stress testing, correction, reset. If that sounds cold, it's because it is. Nature is cold too, and the records are consistent. On one point, modern retellings avoid. Intervention was rare, and always late. Never to prevent collapse, only to preserve continuity. That distinction matters. Flood narratives never save cities. Fire narratives never stop ignition. Dark age stories never halt regression. They preserve seeds. This is why the survivors always seem prepared. They have boats. They have stored grain. They have knowledge compressed into ritual, story, symbol. They weren't chosen at random. They were positioned. And positioning requires awareness. Which brings us to a question that terrifies modern frameworks. What indicators would trigger positioning today? Not morality, not belief, not politics, but functional value. Who preserves knowledge when networks fail? Who can rebuild without industrial supply chains? Who understands systems without needing constant energy input? The answer is not who is richest, it is who is least dependent. This explains why ancient survivors were often described as living on margins. Highlands, islands, remote valleys, deserts, places outside centralised systems. Margins survive collapse better than cores, always have. Modern civilization did the opposite. It eliminated margins, urbanised them, connected them, standardised them. We turned the entire planet into a core, which again suggests that if oversight exists, this cycle is different. There are no untouched margins left, no independent refugees, no parallel civilizations, which means if a correction occurs, it will not be regional. It will be global, and global correction cannot rely on physical relocation alone. It would require information-based survivorship, data that can persist through collapse, skills that don't require infrastructure, knowledge that compresses efficiently. This is why ancient cultures encoded survival information in stories rather than texts. Paper burns, stone erodes, but narratives propagate. They embed instructions invisibly. Build high, follow the stars, store seed, watch the water, not commandments, reminders. So here is the part people resist the most. If watchers exist, and if cycles persist, then modern humanity is not being judged. It is being measured. Measured for adaptability, measured for restraint, measured for awareness. And measurement does not require intervention, only observation, which means the silence people interpret as abandonment could be intentional. The experiment only works if participants believe they are alone. Otherwise, behaviour changes, responsibility diffuses, dependency returns, and the system never stabilises. This would explain something deeply unsettling about our era, why discovery accelerates precisely as instability increases, why climate data sharpens while response slows, why warning signals grow louder as action becomes harder. This isn't conspiracy, it's behavioural physics. Systems under observation behave differently when they know they're watched, so they aren't told. They are left to reveal themselves, which leads to the final fork in the road. If collapse is inevitable, then meaning lies in preservation. If collapse is avoidable, then meaning lies in restraint. Either way, the ancient lesson is the same. Civilizations don't fall because they're evil. They fall because they exceed the limits that made them possible. The only real question left is whether awareness can override momentum, or whether the seventh civilization will do what all six before it did. Assume it's different. Assume it's exempt. Assume it's final. And leave nothing but fragments for the next survivors to piece together. Then the eighth civilization doesn't begin with fire. It doesn't arrive with cities collapsing overnight or oceans swallowing coastlines in a single breath. That image is comforting in its clarity. Catastrophe feels decisive. It gives us an ending we can recognize, but history suggests something quieter. The eighth civilization begins before the seventh realizes it is ending. It forms in parallel. Every previous cycle left behind a thin layer of people who adapted early, not after collapse, but during instability. They didn't wait for permission. They didn't wait for consensus. They adjusted their lives to conditions others still denied. Not rebels, not prophets, observers. They noticed when systems became brittle, when supply chains replaced skills, when efficiency replaced redundancy, when convenience replaced resilience. The eighth civilization begins with people who stop optimizing and start buffering. They don't look impressive. They don't dominate platforms or headlines. They quietly learn how to do things without infrastructure, grow food without global inputs, store water without grids, preserve knowledge without servers, communicate without reliance on fragile networks. These are not survivalists in the cinematic sense. They are archivists of function, and they appear in every collapse record. In Rome's fall, they were monks copying texts while cities decayed. In the Bronze Age collapse, they were craftsmen who retained metallurgical knowledge while trade networks vanished. In post-classic Maya decline, they were farmers who preserved seed diversity when urban centres failed. The pattern repeats because it works. The eighth civilization is not a reboot. It is a handoff. And handoffs require compatibility. This is why advanced civilizations do not leave behind blueprints for skyscrapers or engines. Those are useless without industrial scaffolding. They leave behind principles, ratios, cycles, calendars, navigation methods, ecological thresholds, knowledge that scales down as well as up. That's the quiet brilliance of ancient encoding. It survives regression, which raises a sobering realization. Most modern knowledge does not. A smartphone contains more data than a medieval library, yet becomes useless without electricity, networks, manufacturing, and specialized repair chains. Our civilization stores intelligence externally. Previous ones embedded it internally. That difference alone may decide survivorship. If the eighth civilization is forming, it is doing so in opposition to modern incentives, not because it hates technology, but because it understands dependency. Dependency creates fragility. Fragility accelerates collapse. So the early eighth civilization behaviours look strange to seventh civilization eyes. People stepping away from hyper-specialization, people relearning manual skills despite automation, people decentralizing energy, food and knowledge, people questioning growth as a metric of success. They are often dismissed as nostalgic, paranoid or regressive. They always are, until they're not. What's different now, and this matters, is scale. There has never been a truly global civilization before, which means there has never been a truly global collapse, and there has never been a transition where everyone is inside the system that's failing. That changes the math. There is no untouched frontier, no empty landmass waiting to be settled afterward. The eighth civilization cannot expand outward. It must condense inward. It must operate smaller, tighter, quieter, less visible. This may explain why so much innovation today happens at the margins rather than the centre. Open source systems outperform proprietary ones. Local energy solutions outperform centralised grids in crises. Peer-to-peer communication survives censorship and outages better than broadcast systems. These are not ideological movements. They are evolutionary responses, and evolution does not ask permission. It tests what works, then selects. Which brings us back to the watchers, real or symbolic. If oversight exists, it would not announce the eighth civilization. It would simply observe which human systems persist under stress, which communities self-organise, which knowledge transfers without authority, which values produce stability rather than acceleration toward limits. In that sense, the test is already underway, not in a single dramatic moment, but in thousands of small decisions made every day. Do we centralise or decentralise? Do we extract or regenerate? Do we simplify or overcomplicate? Do we rely or remember? Every answer nudges the trajectory, and trajectories don't change suddenly. They curve, slowly at first, then all at once. The most unsettling implication is this: the seventh civilization may never experience a clear end. It may simply lose relevance, its systems too rigid to adapt, its values too mismatched to conditions, its scale too large to pivot. Meanwhile, the eighth civilization grows quietly in its shadow, smaller, more modular, less ambitious, more durable, not utopian, not perfect, just survivable. And if the pattern holds, thousands of years from now, someone will uncover fragments of our world, satellites fallen from orbit, cities half buried, data centres turned to stone shells. They will wonder how such a powerful civilization vanished. They will find our myths confusing, our priorities strange, our faith in endless growth naive. And they will likely repeat the same mistake we are tempted to make now, assuming the collapse was sudden. It wasn't. It was gradual. And it began the moment we stopped listening to the warnings encoded by those who came before us. This is where the story ends, not with destruction, but with a choice that never feels dramatic enough to matter. Whether we cling to the seventh civilization's momentum, or quietly prepare to become compatible with the eighth. The earth does not need permission to continue. History does not need witnesses to repeat. But awareness, real awareness, has one rare advantage. It allows us to step out of the centre of the cycle, not to escape it, but to survive it with intention. And that may be the only legacy that ever truly lasts.